Confession time. The universe keeps punking us. Every time we think we've got the grand story straight, it flips the table, grins, and says, try again. If you've ever argued about directions with a friend who swears they're never wrong, yeah, space is that friend. So tonight, forget the textbook voice. Picture a late-night booth, coffee that tastes like ambition, and a napkin full of doodles that might change how you see everything. Our mission isn't to worship old answers. It's to chase the moments when reality taps the mic and goes, plot twist. We'll poke at sacred cows, kick the tires on big ideas, and follow the breadcrumbs left by light that's been traveling longer than civilization has existed. No gatekeeping, no jargon parade, just the thrill of catching the cosmos mid-wink. Here's the promise. By the end, you won't just know a few shiny facts. You'll feel how the game is played, how curiosity breaks in, how doubt cleans house, and how being wrong is the cover charge for getting closer to the truth. Bring your best questions, your healthy skepticism, and maybe a snack. The universe is vast. Our attention span isn't. Let's make every minute count. The biggest discoveries start with a raised eyebrow and the guts to say, hold up, what if we're wrong? You know that friend who tells a story with total confidence, and then someone pulls up the texts and the timeline tilts by 5 minutes. Cosmology is that friend, but the receipts are written in light. So let's keep this late night and human. 2 people in a booth, coffee gone lukewarm, napkin doodles getting ambitious. The simplest picture to keep in your head is that space itself stretches. It's not galaxies firing tiny rockets through a static room. It's the room getting bigger under everything at once. If you want a kitchen counter image, think dough rising in an oven and galaxies as the raisins drifting apart because the dough swells. When astronomers say the universe is expanding, they're talking about the dough, not the raisins. And when they talk distance, they lean on a unit called the light year, which is just how far light travels in a year, an absurd count of kilometers. But the only part you truly need is that bigger distance means older light. In the cosmos, distance doubles as a time stamp. So every faraway galaxy is a message in a bottle postmarked ages ago. There's a second trick that sneaks into the story the moment you care about motion. Light has a color, and that color, technically its wavelength, gets stretched if space stretches during the journey. That slow slide toward the red end of the spectrum is called redshift. It's the same idea as an ambulance siren dropping in pitch as it drives away, just done with color instead of sound. Read enough redshifts and you don't just collect distances. You start to see a pattern in how quickly out there seems to be receding as a function of how far it is. Bundle that pattern into one nowish number, and you have the Hubble constant, how many kilometers per second of extra separation you get for each megaparsec of distance. A megaparsec is about 3 million light years, big cosmic block. The exact value matters, the units matter, and so does the fuzz around the number. Astronomers don't say it is X and walk away. They say it's about X plus or minus a bit, because pretending the fuzz isn't there is the fastest path to being confidently wrong. If you've heard people mutter about attention, this is what they mean. There's a road to that expansion number that starts with the universe's baby picture, the cosmic microwave background, a faint afterglow from when everything cooled enough for light to travel freely, a few 100,000 years after the beginning. Read the pattern in that glow carefully, and you can reconstruct the early mix of ingredients and the geometry of space, well enough to predict what today's expansion ought to be. There's a different road that starts close to home and builds, outward using objects whose brightness can be standardized and trusted, like specific exploding stars. That ladder of distances measures expansion more directly in the nearby universe. Both roads are careful. Both quote uncertainties that are only a few percent. And yet the nearby road tends to land a little higher than the baby picture road, roughly low to mid 70s in kilometer per second per MPC versus high 60s, if you want a ballpark without fussing over decibels. The spread is bigger than you'd expect if it were just random noise. That's the "we need to check our pockets" moment. Maybe the ladder has a scuffed rung that makes everything lean. Maybe the early recipe needs a pinch of something extra. Maybe part of what we thought was settled isn't fully settled after all. No melodrama, just a clue. The distance ladder is exactly what it sounds like. You anchor the bottom rungs with nearby things whose distances you can determine without assumptions. You calibrate slightly farther markers against those, and you keep stepping outward. Certain pulsing stars called Kiphides have a pattern that lets you infer their true power. Certain supernovae erupt with a brightness that can be standardized. The trick is to cross-calibrate each rung so a tiny bias down low doesn't balloon into a big mistake higher up. Dust can dim light. Environments can tweak how a star behaves. Known brightness can have caveats that only show up when you push your sample from dozens of galaxies to thousands. That's why the most honest plots come with error bars, little lines that say how wide the confidence window is and why people argue about 1% corrections like they're fighting over the last life raft. If you don't like candles and explosions, there's an almost poetic alternative, a ruler carved into the universe by itself. In the very early plasma, sound waves rippled through matter and light like the thump of bass in a crowded room. When the cosmos cooled and those ripples froze into the distribution of matter, they left a preferred spacing of faint, statistical bump in the distance at which you're slightly more likely to find pairs of galaxies. Measure that bump across the sky, and you have a standard ruler that's been expanding with the universe. The method's fancy name, baryon acoustic oscillations, hides a simple spirit. Space left us a yardstick, and we can read it. Because this ruler ties back to the same early physics that shaped the baby picture, it tends to agree with that lower expansion number. Agreement between two methods with different bad habits is comforting. It doesn't settle everything, but it tells you you're not hallucinating. There's a third opinion you can ask for by watching how mass bends light. Gravity curves space, light follows space, and big clumps like galaxy clusters act as lenses. Map the distortions, and you can weigh invisible mass directly, sketching the cosmic scaffolding that visible matter drapes over. In dramatic cases, one background object is split into multiple images that arrive at slightly different times because the roots are different lengths. Those time delays aren't just party tricks. If you understand the lens well enough, the delays tell you about distance and hence about expansion. Lensing is messy because real galaxies are not perfect laboratory lenses, but it's honest in a different way. It doesn't care how bright something should have been, only how space itself is shaped. Some of those lensing-based expansion measurements line up with the faster local value, which keeps the conversation interesting. The responsible reaction isn't to cherry-pick your favorite choir member. It's to make the microphones and acoustics so good that you can hear who's actually off-key. All of this rests on a broader story that people love to either oversell or undersell. The broad strokes are solid. Space is expanding. The ancient afterglow exists and is full of information. Gravity is doing more than the bright stuff can explain, which means there's extra mass we don't see, or the rules of gravity shift a hair on the grandest scales. The expansion sped up in the last half of cosmic history, which means there's some kind of gentle push baked into the fabric of space. None of those sentences requires equations to make sense. The words do need a little translating, though, because two of them sound like sci-fi. Dark matter isn't a ghost. It's more like an unlit elephant. You don't see it shine, but you feel its pull in how galaxies rotate, in how clusters jiggle, in how lensing maps the weight of invisible halos around galaxies. Treating it as a new kind of matter that ignores light but obeys gravity ties together a lot of independent clues in one move. It might turn out to be several things rather than one thing. That's fine. Dark energy is the other half of the spooky duo, and the name makes it sound like a potion. It's simpler than that. Distances to faraway objects come out bigger than they would in a universe that was only coasting or slowing, which means the expansion is accelerating. The cleanest explanation is a constant energy density in space itself, something that doesn't dilute as the cosmos grows. If future data say it wiggles with time, we'll roll with that. But the headline acceleration is not hanging by a thread. If it feels like I'm dancing around numbers, it's because the precise numbers evolve with better measurements, and the goal here is to give you the logic so you can follow the dance, not to tattoo today's decimals on your brain. Still, units matter, and so do uncertainties. When someone quotes an expansion rate, the unit kilometers per second per megaparsec is telling you a slope. For every cosmic block of about 3 million light years, the recession speed goes up by so many kilometers per second. And when they append give or take, that's not an escape hatch. It's the honesty tax. Two teams can disagree and both be within their quoted fuzz. But when the centers of those fuzz clouds keep sitting apart more than chance can justify, that's when you raise an eyebrow and start checking for either a hidden bias or a hint of new physics. You can't spend long in this topic without bumping into human process. People argue with themselves by design. They run blind analyses where the final numbers are hidden until all the choices about cleaning the data are frozen, so nobody can unconsciously nudge the method toward their favorite outcome. They simulate fake skies to make sure their software doesn't invent patterns from noise. They swap data and try to break each other's conclusions. From the outside, it can look like stubbornness. From the inside, it's hygiene. Richard Feynman's line, "Nature cannot be fooled," it's pinned above a lot of whiteboards for a reason. It's not cynicism. It's protection against falling in love with your first draft. A particularly juicy twist in the last few years has been the number of surprisingly grown-up galaxies, spotted very early in the timeline. It's like walking into kindergarten and noticing a couple of fourth graders calmly doing long division. That doesn't wreck the school. It forces you to ask whether your assumptions about how fast stars form in those conditions were too conservative, or whether the early universe gave structure a tiny head start that your models hadn't included. The first is an astrophysics fix. Maybe those early pockets of gas were more fertile than we thought. The second leans toward a cosmology tweak. Maybe there was a brief, subtle phase of extra energy early on that helped clumps form faster without breaking the rest of the map. A quieter possibility is selection bias. The show-offs are easier to spot first, and the quieter majority will fill in as the surveys deepen. The right response is patience paired with precision. More light, cleaner samples, better accounting for every mundane effect that can masquerade as a miracle. If you want a one-sentence philosophy to carry into the rest of this series, try this. Models are tools, not scripture. They earn trust by surviving contact with messy data from different angles. A pretty idea that trips over new measurements is just a poem with bad facts. The current map of the universe deserves respect because it keeps delivering predicting patterns we then see, linking phenomena that looked unrelated, telling a coherent story with a small set of ingredients. Respect, though, isn't worship. When the map and the territory argue, the territory wins. That's not a failure. That's the scientific method doing the dishes. Where does that leave us at the end of this session? With a living map that works in broad strokes and a couple of stubborn details that refuse to harmonize. The expansion is real. The ancient glow is real. The invisible scaffolding is, in one form or another, real. The late-time push is real. The exact speed today, as read by different traditions, isn't perfectly agreed upon, and a handful of early galaxies look ahead of schedule. That's not a crisis. That's a to-do list. Maybe a tiny calibration in the local distance ladder gets tightened, and the two camps finally shake hands. Maybe a crisp new measurement of the early pattern narrows the baby picture prediction and pushes it toward the local one. Maybe a subtle early time ingredient earns a permanent place in the recipe because it fixes the tension without breaking anything else. All three are reasonable, and the way we choose among them is simple if not easy. Build better instruments, take deeper surveys, argue with more discipline, and let the numbers, not the vibes, decide. And yes, there's joy in the slog. There's joy in the fact that humans can tell the difference between a bit under 70 and a bit over 70 when talking about the speed at which all of space stretches per cosmic block. There's joy in disagreements that make both sides sharpen their tools. There's joy in watching the sky hand us problems that are exactly the right size for a curious species with limited attention spans and unlimited audacity. If the title of this film sounds like a provocation, that's because it is. But the answer to it isn't a theatrical "everything was wrong" or a defensive "everything is fine." It's something more interesting. The skeleton of the story stands, and the best parts of science live in the arguments over the details. That's where progress hides. That's where the next chapter starts. You can tell a lot about a city by how the traffic sounds through a half-open window at midnight. Cosmology is like that, except the window is a telescope and the traffic is light that's been on the road for billions of years. After our first round, where we set the table with expanding space and those stubborn numbers that won't quite agree, let's lean in on how we turn light into a timeline without pretending we've got magic powers. The key is that distance in the universe doubles as a clock. Light doesn't teleport. It cruises at a fixed speed. So when you catch a whisper of a galaxy that sits, say, billions of light years away, the phrase light year is pulling double duty, telling you how far and how long. Astronomers call the how long piece the look back time, which is just a fancy way of saying how far back the message in the bottle was written. There's another flavor of distance that's useful once you start mapping whole surveys called comoving distance, which you can picture as the yardage between 2 points if you pause the cosmic stretching and draw a grid on space. You don't need to memorize the jargon. What matters is that we have a clean way to keep track of where and when, even while the room itself keeps getting larger under our feet. Now, the baby picture of the universe, the cosmic microwave background, isn't just cute. It's strangely talkative. It's the afterglow from when the universe was a few 100,000 years old and finally cool enough for electrons and protons to settle down into neutral hydrogen, so light could travel without being constantly bounced around. Before that moment, the cosmos was a foggy soup. After it, it becomes a transparent room where light can head out on a long road trip. If you look closely at that afterglow with a good enough camera, it's not perfectly smooth. It has tiny hot and cold freckles, and those freckles are a fossilized weather map. Imagine sound waves rippling through the early plasma, the way bass ripples through a packed club. The crests and troughs of those waves got frozen into the pattern we see. When people say the baby picture measures the recipe, that's what they mean. The size of those ripples and how tall. The different ripples are compared to each other, tell you about the mix of ordinary matter, the invisible matter that only shows up through its gravity, and the overall geometry of space. Once you've got that early recipe, you can press play on the cosmic clock and ask, if this was the starting mix, how fast should the room be expanding now? That's the move that gives one of the two competing expansion speeds and sets the stage for the argument. The baby picture isn't the only early receipt we keep in the drawer. There's also a snapshot from the first few minutes after the beginning called primordial nucleosynthesis, which is a mouthful that means light elements were forged when everything was still blisteringly hot. In those opening minutes, the universe made most of its helium and traces of deuterium and lithium, and the exact amounts depend on how much ordinary matter there was per cubic meter. Much later, you can measure how much of those elements still exist in places the cosmic kitchen hasn't stirred too much. And that measurement lines up with what the baby picture says about the same ingredient. Two very different clocks, two very different thermometers, and they tell the same story within the fuzz. That kind of cross-check is why cosmologists sleep at night, even when two numbers elsewhere won't shake hands. After the baby photo, the room goes dark for a while. People call it the Dark Ages, but it's not spooky. It's just that there were no stars yet. Eventually, gravity wins enough small contests to light the first stars and small galaxies. And when those stars start shining, their harsh ultraviolet light breaks apart the newly minted neutral hydrogen, reionizing the universe. You can think of reionization as the moment someone flips the city lights back on after a blackout. That transition leaves hints in the polarization of the baby afterglow and, in principle, in a cool radio whisper called the 21-centimeter line from hydrogen itself. That radio whisper is ridiculously hard to hear because our own planet is loud and messy. But it's worth mentioning because if we map it well one day, it's a direct timeline of how the fog lifted and where the first neighborhoods took shape. The point of all of this is not to drown you in eras, but to show that we don't lean on a single photograph. We follow a trail of breadcrumbs, each one stamped with a date and a place. Once stars and galaxies start showing up in force, the story becomes a tug of war between gravity and energy, and the players show their personalities. The unlit mass we call dark matter clumps under gravity, like flour lumps forming in batter. The ordinary matter, because it can bump into itself and cool by radiating light, falls into those dark matter clumps and makes the stuff we can see. How quickly that happens depends on things that are both cosmic and local. On the cosmic side, you've got the expansion trying to pull everything apart, and later on, that gentle push we call dark energy, making the pull even harder. On the local side, you've got star formation turning cold gas into suns, and then those very stars exploding and shoving on the gas, sometimes shutting down future star making in that neighborhood. Black holes at the centers of galaxies get a say too. As they feed, they can fling out energy that heats or ejects the gas you'd need to make more stars. This messy feedback is why modeling the exact timeline of how galaxies grow is so hard. It's not enough to say gravity clumps. You have to say how quickly the gas cools, how violently stars and black holes punch back, and how those punches echo through the next rounds of growth. It's also why those early, surprisingly beefy galaxies caused such chatter. Either the kitchens back then were more efficient than we thought, or the room's overall rules gave clumps a head start, or we're mostly seeing the show-offs and the quiet ones will fill in later. All three are reasonable reactions, and the way to choose is boring and beautiful. Gather more light from more objects with better calibrations, and let the statistics do their job. Speaking of calibrations, the distance ladder deserves a fair shake, because it's where a lot of adult arguments are living right now. The bottom rung is geometric. You watch a nearby star shift its apparent position against the background as Earth moves around the sun. A simple triangle that gives you distance with no astrophysical assumptions. Space missions that measure this parallax with insane precision anchor the whole ladder. Once you know the true distances to enough nearby landmarks, you can calibrate the candles. Kiffide variables, the stars that pulse in a very regular way, are a classic rung because their pulsation period ties neatly to their true brightness. If you know how bright they really are and how bright they look, you can work out distance. The way you could guess how far a streetlight is if you knew its wattage. Farther out, certain supernovae explode with a brightness that can be standardized by looking at how their light fades, which lets you extend the reach of the ladder deep into the cosmic suburbs. There are parallel routes too, like using the tip of the red giant branch, which is the moment certain aging stars hit a predictable brightness before changing character. That trick is less sensitive to the messy environments inside galaxies, where dust and young stars can complicate the read. And there are geometric anchors off the beaten path, like water masers, orbiting the centers of a few lucky galaxies that draw perfect circles you can clock, giving you a distance with pure geometry. Every rung has a personality. Every rung has a way to go wrong. Dust can dim light in ways that mimic distance. The metal content of a star can shift how it behaves. Selection effects can make you preferentially pick the easy-to-spot cases. None of this is scandal. It's carpentry. You sand the rung. You check it against the one below. You don't let one weak step set the tone for the whole staircase. While the ladder community polishes their steps, there's a parallel movement to bring completely different rulers to the party, so we're not stuck eating from one kitchen. Those ancient sound wave ripples baked into the large-scale pattern of galaxies' baryon acoustic oscillations give you a ruler that grows with the universe. If you can measure how wide that ruler looks at different redshifts, you can back out how distances scale with time, which is another path to the expansion story. In the same spirit, weak gravitational lensing, which is the barely perceptible stretching of galaxy images across huge swaths of sky because of all the mass in between, lets you weigh the scaffolding of the universe without caring how bright anything is. That measurement has its own headache. Shapes of galaxies have to be measured exquisitely, and your telescope's camera smears things in ways you need to model with embarrassing honesty. But when it sings a different harmony from the candles and the rulers. Then there's the new kid with a promising voice, gravitational wave standard sirens. When two neutron stars spiral together and merge, they send a ripple through space-time that acts like a shout whose loudness tells you how far away it happened. If you can also get a redshift by catching light from the event or by pinning down which galaxy it came from, you get a distance redshift pair that skip the whole candle game. There aren't many of those events yet, and they're not super precise one by one. But as the count grows, they could become a clean, independent referee in the expansion debate. The beauty of these parallel routes isn't that any one of them is perfect. It's that they fail differently. Agreement feels earned. Disagreement tells you exactly where to pry. A quick aside that sounds fussy and matters a lot is cosmic variance. It's a polite way of admitting that the universe is one actual thing, not a statistical playground where you can roll the dice a million times under identical conditions. If you map a patch of sky the size of a fist, its particular clumpiness will be a little above or below the average just by chance, and that randomness bleeds into your measurements. The cure is to go wide, to map huge areas so those local quirks even out. It's why modern surveys try to cover big slices of the sky rather than one jewel box patch. And it's yet another reason the field can't do quick answers. Big areas take time. Big areas demand pipelines that can handle everything from the glow of our own atmosphere to a fingerprint on a lens. The impatience is human. The need to go slow is written into the sky. You don't need me to tell you that the phrase dark matter sounds like a mood and dark energy sounds like branding. But behind the awkward names are clean, testable statements. The unlit mass is a bookkeeping necessity born from watching how stars and galaxies move and how light bends around them. Either there's more mass than we can see, or the rules of gravity change at large scales. The first option is less dramatic and ties many different clues together in one tidy bow. The second is bold and not dead on arrival, but it has to thread needles across the baby picture, the galaxy patterns, the lensing maps, and local dynamics without coming apart. That's a high bar. As for the gentle push that speeds up expansion, the simplest option is a constant energy built into space itself, which sounds mystical and is really just bookkeeping again, a number that says how much push per cubic meter, not diluting as the universe grows. If future measurements show that the push drifts slightly with time, that's not a betrayal of the idea. It's a refinement. The way gravity is an attractive force becomes gravity is the shape of space-time when you need to be precise. When people get antsy and ask for a verdict on the expansion fight, you can feel the tug to pick a team, but the adult answer is that we're still doing the homework. Either the local ladder has one or more tiny biases that add up to a noticeable lean, or the bridge from the baby picture today needs an extra plank we haven't installed. A favorite plank in the rumor mill is a short-lived phase of extra energy early on, that would shift how the ancient ripples translate to today's ruler length without wrecking the rest of the fit. Another is the idea that the invisible sector dark matter, talking to dark energy in some subtle way, might give the right nudge. Those are just ideas on the table. They don't get promoted because they sound cool. They get promoted if future data corner them into being the only sensible way out. The history of physics is extremely clear about this. Most tensions resolve into better calibrations and more careful bookkeeping, and once in a great, while you get a genuine upgrade to the playbook. The only way to tell which you're living through is to keep measuring and to keep trying to break your favorite explanation. There's a social piece to all this that never makes headlines and quietly decides everything. Teams run blind where they can, so the final answers are hidden until all analysis choices are locked in. They swap data to see if an independent pipeline gets the same number. They publish boring appendices about how they modeled dust or corrected a detector quirk, because those boring pages are where most fake revolutions go to die. It looks fussy, and it is, and it's also why the field succeeds. You don't want a community that falls in love with its own story. You want one that treats the story like a draft and the sky like an editor, who doesn't care how charming your prose sounded in the first pass. So here we are, at the end of another long coffee, still in the part of the movie where the clues are piling up and the detective's notes are a mess. But you can feel the threads starting to braid. The expansion is real. The baby picture is a gold mine. The unlit scaffolding is doing work, whether it turns out to be a particle or a paragraph in the gravity textbook. The late time push is a thing we measure rather than a vibe we claim, and a few details refuse to sit quietly in the corner. That's not a crisis. That's a good Tuesday in a field that argues with light for a living. The way forward is not a plot twist. It's the slow, satisfying work of better distance anchors from parallax, more galaxies in the standard ruler maps, sharper lensing that weighs the invisible with cleaner statistics, and new voices like gravitational wave sirens growing from a novelty into a chorus. Someday not too far from now, the numbers will either pull together because we sanded the right rung on the ladder, or they'll keep drifting in a way that forces us to add that extra plank to the early recipe. Either way, the skeleton stays, the posture improves, and the view gets a little cleaner the next time we press our faces to the glass. Remember when everyone knew the universe was slowing down? Gravity pulls. That's its whole personality. If you toss a ball upward, it rises, stalls, and comes back because the pull never quits. For decades, the cosmic version of that story felt inevitable. Space is expanding, sure, but the combined gravity of all the matter should be tapping the brakes. Then the late 1990s happened, and a bunch of astronomers pointed their telescopes at special stellar explosions, type Ia supernova, the kind that, for well-understood reasons, reached nearly the same peak brightness, and used them as distance markers. The game is simple enough to explain at a table. If you know how bright a bulb truly is, you can figure out how far away it is from how dim it looks. Pair that distance with a redshift. The way the light's color is stretched toward the red, because space expanded during the journey, and you get a point on the cosmic speedometer. Stack enough points at different redshifts, and a pattern emerges. What they saw was not a gentle slowdown. The distant bulbs looked dimmer than a coasting or decelerating universe would allow. Dimmer meant farther. Farther at that redshift meant the expansion had sped up. That's acceleration. It landed like a plot twist because it flipped the sign on what we thought gravity was doing to the grand story. You could practically hear textbooks clearing their throats. It wasn't a decision made over a single espresso. People kicked the tires until the rims squeaked. Dust can imitate distance by dimming light in sneaky, wavelength-dependent ways. So the teens checked the colors to make sure the dimness wasn't just soot in the universe's chimney. Maybe the explosions were different in the past subtle changes in the stars. Composition can tweak how bright these supernovae get, so they built calibrations that account for that, and cross-checked with nearby samples, whose distances are known by geometry. Maybe we were just seeing the loudest examples at each distance because of selection effects. The show-off's first Shrapso, they modeled that too. The result, after years of this unsexy calibration obsession, was that the effect refused to vanish. Distances to faraway supernova really were a bit larger than you'd expect in a universe that merely coasted or slowed. The acceleration wasn't a vibe. It was a number that survived the usual suspects. The simplest way to encode that number into physics sounds almost mystical and is really an accounting decision. Imagine space itself carrying a tiny uniform energy in every cubic meter. Not a gas, not a field that clumps, just a steady background hum that doesn't thin out as the universe grows. Ordinary matter gets more dilute as space expands. This stuff doesn't. Give that something a push-like effect, negative pressure in the technical language. But you don't need the term, and it makes gravity act a little weird on the biggest scales, turning the overall expansion from braking to gently accelerating. If you prefer metaphors, it's like realizing your car has a cruise control you didn't know was on. You can fight it with the pedals in the short term, but the background nudge keeps asserting itself. People nicknamed this background energy a cosmological constant because, if that's what it is, its value doesn't change with time. Later, as better data piled up from the ancient afterglows pattern to the way galaxies spaced themselves out, you could fit everything consistently with a picture where most of the cosmic energy budget is this quiet, uniform push, and a big chunk of the rest is the invisible mass whose gravity shapes structure. It's not romance, it's bookkeeping that lines up. Of course, the minute you put constant into the story, theorists start asking whether it might actually be something that evolves, a field that changes slowly over time, rather than a hard-coded number. You can feel the pull of that idea because it lets the push be dynamic, perhaps stronger early on and mellower later, or the other way around. If reality went that route, it would change the exact way distances scale with redshift, and patient astronomers would see the fingerprints in big surveys of supernova and galaxy patterns, and in subtle features of the ancient glow. That's not a solved argument, it's an open invitation. The most honest summary today is that a true constant fits the data pretty well, and any drift over time would have to be small enough to hide in the fuzz of current measurements. Small doesn't mean uninteresting. It just means you need cleaner microphones before you claim the singer changed keys. Meanwhile, the accelerating story doesn't live alone. It intertwines with everything else we've been talking about, because changing the pace of expansion changes the schedule for when structures form. If space stretches faster at late times, gravity has less time to gather matter into new galaxies, which in turn tweaks how rapidly star formation tapers off in the cosmic timeline. That means you can cross-examine the acceleration not only with distance markers, but also with the growth of clumpiness in the universe. Astronomers do this by watching how the shapes of millions of background galaxies get slightly stretched weak gravitational lensing by the mass in front of them. The statistical pattern of those stretches tells you how quickly structure has been building up. If the buildup is slower than expected while the expansion is faster, that's a coherent story. If it's faster and faster, someone's model needs an appointment with the shop. The thrilling, maddening part is that different surveys, built with different cameras and data pipelines, sometimes whisper slightly different answers. You don't slam the table, you take another breath. You remeasure the shapes, you argue about whether your atmosphere model is good enough. You check whether your selection of galaxies accidentally favored a weird subset, and you keep going until the disagreements either evaporate or harden into a real clue. There's a human angle to this twist that always gets me. Two rival teams chasing the same faint fireworks in distant galaxies, comparing notes and notepads, swapping calibration stars like recipes, then converging on the same inconvenient truth. The universe wasn't just cruising, it was pressing the gas. The prize committees loved it because it was clean, surprising, and decisive, But the day-to-day reality was less Hollywood and more spreadsheets and long nights. The reward wasn't just the headline. It was the way that one result stitched together with the baby picture and the galaxy ruler in a story. That made sense from minutes after the beginning to billions of years later. When independent roads built on different assumptions agree, your shoulders drop a little. You still worry, because worry is a professional habit, but you worry with better posture. If you're wondering how big the acceleration is in practical terms, think in slopes rather than speeds. The expansion rate today, the Hubble constant, is quoted in kilometers per second per megaparsec because it's a gradient. For every chunk of about 3 million light years, the recession speed ticks up by that many kilometers per second. A universe that coasted would give you one mapping from redshift to distance. A universe that accelerates gives you a mapping with a higher redshift distances, come out larger by a few to several percent over the redshift range the supernova probe. Those percent level differences are small enough to hide behind sloppiness and large, enough to stand out once your error bars are honest. That's why this whole conversation was even possible over a couple of decades. The measurements got good enough that could be either wasn't a respectable answer anymore. What I love about the acceleration story as a case study is how it teaches the right instincts. Start with a clean question you can actually measure. Chase down the boring ways you might be fooling yourself: dust, evolution, selection, before you declare victory. Invite other orthogonal methods to check your work, even if they come from completely different parts of the cosmic timeline. Prefer the explanation that adds the fewest moving parts while matching the most observations. And keep an eye on whether that explanation still holds when you bring in fresh data a decade later. And be prepared for the universe to make you say a sentence that felt forbidden in class. It's not slowing, it's speeding up. All of that loops back to our theme. Being wrong in the right way is how the map gets better. The pre-90s expectation that gravity would break the expansion wasn't foolish. It was the best extrapolation from the tools and data of the time. The supernova didn't humiliate that picture. They framed it, pointed to the gap, and said, "Look here." The fix in energy that acts like a steady push per cubic meter of space wasn't pulled from thin air. It was a minimal patch that made 3 independent lines of evidence agree without turning the rest of physics into a circus. If it turns out that the push slowly drifts with time, or that the invisible sector has more personality than we gave it credit for, fine, we'll update again. That's not failure. That's the fee you pay for asking big questions with real numbers. If the accelerated expansion was the plot twist, dark matter is the quiet character who's been on screen the whole time and only now gets a monologue. The name sounds theatrical, but the role is practical. There's more gravity in and around galaxies than the bright stuff stars, gas, glowing dust can supply. You don't have to take it on faith. You can hear it in the way galaxies spin. Imagine watching a merry-go-round at night with tiny lanterns on the horses. From the lanterns, you'd guess the mass is concentrated toward the center, so the outer horses should move more slowly, the way planets far from the sun take longer laps. But when you measure actual galaxies, the outer stars aren't dawdling. Their speeds stay stubbornly high, tends to a couple of 100 kilometers per second, even far out in the disk, as if an unseen halo of mass is pulling on them. That same extra pull shows up in clusters of galaxies, which are like small towns bound together by gravity. The galaxies inside buzz around faster than the visible mass alone can justify, and the hot gas between them is held more tightly than starlight would predict. It's the same whisper over and over: "You're missing weight." Light itself backs this up in a wonderfully literal way. Gravity bends space, light follows space, so a fat halo around a galaxy acts like a lens and warps background images. Sometimes you get dramatic arcs and multiple images of a single faraway galaxy. More often you get delicate, barely perceptible stretches in the shapes of thousands of background smudges. Stack enough of those stretches and a map emerges. Big cocoons of invisible mass cradling the places where stars live. There's nothing mystical about the map. It's geometry with patience. The pattern of how matter clumps on very large scales hundreds of millions of light years tells the same story. There's a scaffolding we don't see, and the luminous structures are the neon signs tracing its beams. When you stitch all these clues together, the spins, the motions in clusters, the lensing, the large-scale clumping, you get a chorus that's hard to ignore. What is the stuff, though? The most boring answer is often the best starting point. It behaves like matter that doesn't care about light. It feels gravity, adds its share to the cosmic weight, but it doesn't emit or absorb photons, so our telescopes only see its effects indirectly. It doesn't care about light. Bit is why it can form those huge, puffy halos around galaxies without cooling and collapsing into a disk like ordinary gas does. On the scales of galaxy neighborhoods and above, that picture knits a lot of independent facts into a single fabric, and that's why it's become the default. It's also why massive computer simulations that start with a smooth early universe and let gravity run end up producing a cosmic web filaments, nodes, voids, looks uncannily like the structures we actually map. If you've ever watched cream pour into coffee and form branching patterns, you've got the right intuition. Gravity makes the cream gather along threads, and the brightest clumps where threads meet are the galaxy clusters. Dark matter is the invisible part of the cream. None of this means the details are nailed to the table. On the smallest scales inside dwarf galaxies and the outskirts of spirals, the default, simple version of dark matter sometimes predicts central density peaks that are sharper than what observers infer, and it forecasts more tiny satellite galaxies around big ones than we initially counted. Those headaches acquired melodramatic nicknames, as if the universe were trolling us. But over the last decade, a lot of that drama deflated once people modeled the ordinary stuff more honestly. When stars form, they don't do it politely. They blast energy into their surroundings, and supernovae are the loudest offenders. That energy can push gas around in ways that soften a sharp central pileup into a gentler one. And if you remove or heat up enough gas, some would-be star factories never get going, which means some predicted satellites stay dark and hard to spot. It's not that the invisible matter vanishes. It's that the visible signposts are dimmer and rarer than the first, simplified models assumed. The lesson is the same one we keep bumping into. The universe rewards humility and punishes shortcuts. Because the name dark matter sounds like a confession rather than an explanation, there's always a parallel conversation running. Maybe gravity itself changes character when you zoom out or slow down enough. Modified gravity ideas are catnip because they promise to keep the elegance of no new substances and explain the galaxy rotation quirk in one go. The catch is that any tweak to gravity must then navigate a gauntlet. It has to handle galaxy spins without wrecking the pristine pattern in the ancient afterglow. It has to reproduce the way light bends around clusters. And it has to grow the large-scale web at the right pace under an expanding background. Some ideas get partway and then trip over a lensing result, or they ace lensing and stumble on the early pattern. It's not that the door is locked. It's that the locks are many and independent. Every time you twist one key and think you've cracked it, another deadbolt says, "Try again." Meanwhile, the matter that doesn't shine camp isn't a monolith. People argue amiably about whether the particles are slow and heavy or lighter and a bit more skittish, whether they occasionally bump into each other or barely notice one another at all. Slow, heavy, and aloof gives you the cleanest match to the big structures. Lighter and more interactive can smooth out small-scale quirks, but risks erasing too much structure if you overdo it. That's a knob you can't just spin by taste. The sky decides how far you can turn it. There's also a whole experimental world underground and under mountains, trying to catch a passing particle in a very quiet detector, or to make a faint interaction show itself in a lab. or to tease out a signature from astrophysical mess. So far, the scoreboard is a collection of upper limits. If it exists, it doesn't do X more than this much, which is not sexy in headlines and is pure gold in practice because it fences the playground. When the search volume gets small enough, you either finally see a blip that repeats, or you admit the particle isn't playing in that sandbox, and you move the hunt. One of the cleanest gut checks for there's really extra mass there claim comes from rare cosmic accidents that separate the invisible matter from the luminous gas. Picture two galaxy clusters colliding at thousands of kilometers per second. The stars mostly sail through without noticing, because stars are tiny compared to the gulf between them. The hot gas clouds slam into each other and stall, because gas cares about gas. If there are big halos of invisible matter, they should behave more like the stars glide through with minimal fuss. So after the smash up you'd expect, the mass peaks to sit closer to the passing galaxies, while the bright X-ray gas lags behind. That's exactly what the lensing maps show in a few spectacular cases. You don't have to learn a new theory to read that picture. The invisible weight followed the galaxies. The bright gas got stuck. Whatever you call the invisible weight, it walks and quacks like matter. Because we're telling this as a bar chat and not a legal brief, it's fine to admit the most likely future looks like refinement rather than revolution. The scaffolding story works across a shocking range of scales and epochs. The places it rubs are the places where the visible physics star formation, supernova feedback, black hole tantrums gets messy. It would be satisfying to say, here's the one simple alternate rule that fixes every rub. But the sky's been unromantic about that. Instead, it keeps rewarding the approach where you add human sweat to the visible processes and let the invisible do its quiet, gravitational job in the background. If a lab detector lights up tomorrow, or a new kind of cosmic messenger points to a specific mass range for the particles, we'll high-five and update the posters. If not, the gravitational case remains a brick wall you can lean on. There's a human texture to this chapter that deserves a toast. Some of the cleanest rotation curves, the plots that show outer stars keeping their speed, came from nights where nothing went smoothly, and the telescope only behaved after someone whacked a stubborn cable. Some of the lensing maps were born in rooms where the coffee machine was older than the grad students, and the arguments about statistical biases lasted longer than anyone's patience. And yet, piece by piece, the picture cohered, galaxies wrapped in halos, clusters wrapped in bigger halos, filaments threading it all together, the luminous pieces lighting up the peaks of an invisible landscape. You don't need to love the name, dark matter, to appreciate the discipline it took to turn weird curves into a working map of what's out there. If you're keeping an internal scoreboard, let it read like this for now. Gravity is telling a consistent story about missing mass across methods that don't share the same weaknesses. Alternatives are worth exploring and keep everyone honest, but they haven't yet cleared all the independent hurdles at once. The open questions live in the character of the invisible, whether it's one thing or a family, whether it occasionally whispers to itself, how warm or cold it really is on the cosmic temperature scale, and in the straightening out of small-scale quirks where ordinary physics is rowdy. None of that takes us back to square one. It just means the map still has pencil lines where one day we'll ink in a sharper coast. If the distance ladder is a street-level survey and galaxy maps are the drone shots, the cosmic microwave background is the baby photo your parents keep on the fridge grainy, unflattering, and somehow packed with clues about who you became. Picture the universe a few 100,000 years after the beginning. Before that moment, it was a fog of light and charged particles constantly bumping into each other. Photons couldn't travel far without getting scattered. Then the room cooled just enough for electrons to hook up with protons, forming neutral hydrogen. The fog cleared, light finally slipped its leash, and that light has been cruising ever since, stretched by the expansion into microwave wavelengths you can't see but we can measure with ridiculous care. When you map that glow across the sky, it isn't perfectly smooth. It's freckled tiny warm and cool patches at the level of a few parts in 100,000. Those freckles are frozen ripples from a time when gravity was trying to pull matter together while the pressure of light pushed back, setting up a cosmic version of sound waves. The sizes and heights of those ripples are the universe's version of a medical chart. The first peak, the second, the third, each telling you something about the patient's build, how much ordinary matter was in the soup, how much of the unlit stuff added gravity, whether space is flat like a table or curved like a saddle, and how fast the early clock was ticking. What's wild, sitting here with a tired coffee, is how much that one messy photo locks down. You can read off the age of the universe to within a sliver of 1 billion years, which is bonkers when you think we're basing it on speckles in a glow older than any star you've ever heard of. You can say, out loud and without blushing, that on the largest scale space is very close to flat, meaning if you drew the biggest triangle you could imagine, the angles would pretty much add to 180 degrees. You can weigh the ordinary matter, the stuff that makes atoms, in units that sound like accountant-speak fraction of the total energy budget, and you can do the same for the invisible mass. You can even let the data tell you about a crowd of lightweight particles that barely interact with anything. We call them neutrinos because their presence tweaks the early ripples in a distinctive way, like extra kids jumping on a trampoline. And when you fold in the polarization of that ancient light, the way the electric field wiggles have preferred directions, you get a second opinion that checks the temperature map without relying on the same systematics. Temperature says one thing, polarization nods, and your shoulders drop a little because two independent microphones heard the same tune. The baby photo also lets you peek at the universe's teenage years. The first stars and galaxies eventually turned the fog back on, ionizing that neutral hydrogen with their harsh ultraviolet light. That reionization era leaves a subtle fingerprint in the polarization pattern, because some of the ancient photons scatter off the newly freed electrons and get their polarization tweaked. It's not a clean billboard. You have to squint through a lot of foreground junk from our own galaxy, but once you tease it out, you get a timestamp for when the lights really came back on. Pair that with deep galaxy surveys, and you start to sketch a timeline. First the glow, then the dark ages, then the switch flip as structure wakes up and starts to shine. It's like reconstructing a party from the playlist in a few blurry photos. The vibe comes together, even if you don't have a perfect video. There's more buried in that baby photo than just a census and a clock. Because the ancient light passes through billions of years of cosmic structure on its way to us, it gets gently deflected by the gravity of all those invisible halos. That means the baby photo is slightly out of focus in a way that you can reverse engineer to build a map of the mass in between a lensing map, but now using the oldest possible backlight. When you compare that mass map to what you infer from galaxy surveys and from the weak lensing of background galaxies, you get a three-way handshake. If two agree and the third is sulking, you know where to pull. When all three point to the same rough level of clumpiness in the cosmic web, you breathe easier. And when one insists the web is a bit less clumpy than expected, you try not to panic and instead ask boring questions first. Is it the camera? The foregrounds? The pipeline? The patch of sky? The baby photo is powerful precisely because its failures would be different from the failures of galaxy catalogs. They don't share the same bad habits, so agreement is meaningful. Of course, there are oddities, and you've probably heard the gossip. People talk about a cold spot, a region on the map that looks cooler than average over a large patch, and about alignments on the biggest angular scales with nicknames that make it sound like the universe is playing a private joke. This is where statistics gets unromantic. If you stare at enough freckles, some patterns will look interesting just by chance, the way clouds sometimes look like dragons. The responsible move is to quantify how surprising a feature really is given all the ways you could have chosen to find it after the fact. and then ask whether independent datasets see the same quirk. Most of the time, the drama deflates under that kind of scrutiny. On rare occasions, a thing refuses to go away, and then it graduates from cute anomaly to possible clue. The point, for our late-night purposes, is that the baby photo is not a Rorschach test. It's a calibrated instrument reading. The fact that we can even argue about a 1 in 100 or 1 in 1,000 fluke in a map of the whole sky tells you how precise the whole enterprise has become. Now, how does all this tie back to our running theme that some of our favorite numbers won't quite agree on the price of coffee? The baby photo doesn't measure today's expansion directly. It infers it by saying, if the early recipe was such and such, and if the laws in between behaved as we think, then today's slope should be this. That chain is only as strong as the ingredients and the in-between physics. If you quietly add a spoonful of something during the early minutes, an extra field, a whiff of energy that fades quickly, you can shift how big the ancient ripples appear and therefore shift what you'd predict for today's expansion when you do the math. That's why people toy with early time tweaks when they're fishing for a way to reconcile the baby picture prediction with the local distance ladder. The bar rule still applies. Simple explanations that match the most data with the fewest moving parts get first dibs. Any tweak has to live through the baby photo's detailed ripple pattern, the polarization crosscheck, the big galaxy ruler etched in the sky, and the late-time growth of structure all at once. It's not impossible. It is a gauntlet. And that's healthy. Gauntlets protect us from falling in love with flashy fixes that crack under daylight. Something I love about the baby photo is how democratic it is. You don't need the biggest telescope on Earth to contribute. You need a clean view of the microwave sky and an unhealthy relationship with foregrounds, our own galaxy's dust and magnetic fields which glow in microwaves and try to catfish you. Teams build multi-frequency instruments and watch the same patch at different colors so they can separate the true ancient whisper from the nearby hum. It's painstaking work and absolutely unglamorous, and it's the price of entry for numbers you can trust. It also means that when different experiments with different detectors and different ways of cleaning the mess converge on the same peak heights and the same polarization wiggles, you exhale. The universe is under no obligation to be simple, but it is under an obligation to be consistent, and the baby photo has been a steady witness for years. There's a final, almost philosophical payoff to staring at this glow until your eyes cross. It teaches humility with receipts. The pattern we see is not our pattern. It's the universe's. We translate it into ages and densities and curves because those translations predict things. We can check later how galaxies cluster, how light bends, how supernova dim with distance, and the checks keep coming back mostly green. Mostly is exactly where the fun lives. The same map that nails the broad outline is also the map that, when combined with other evidence, leaves us with that nagging mismatch in the expansion rate and that puzzle about a few early galaxies looking ahead of schedule. The right reaction isn't to declare the map wrong. It's to let it set the baseline while we test whether the latter needs sanding or the early recipe needs one more ingredient. So if you and I step out of this booth and someone asks what the baby photo really gave us besides a cute nickname, you can say this without blinking. It gave us the scaffolding of a story that runs from minutes after the beginning to now, pinned down with enough precision that percent-level disagreements stand out like a squeaky floorboard. It told us the room is basically flat. The age is about 14 billion years, give or take a breath. The invisible scaffolding outweighs the bright furniture by several to one, and a quiet push has been steering the late-time expansion. It also gave us a way to test any new clever idea against a pattern that is maddeningly hard to fake. That's why the field treats it like a reference track. If your remix doesn't sync to this beat, it's not the beat that's wrong. If the baby photo on the cosmic fridge gave us the recipe, the next drama is tasting the cake way earlier than we thought it would be baked. That's the vibe of the early galaxy story that set everyone buzzing. New eyes on the sky started, spotting galaxies so soon after the beginning that they looked a little too grown-up for their age. When astronomers say soon, they talk in redshift, this number we get from how much light has slid toward the red during its trip because space stretched. Bigger redshift means earlier times. If someone drops Z10, think roughly 500 million years after the beginning. Z15 is closer to 300 million years. Those are baby photos of baby photos. And yet, in some of those frames, a few galaxies looked beefy bright, massive, bursting with stars like fourth graders sitting in a kindergarten class. Before we panic, it's worth walking through how we even know a distant smudge is that far away. The first pass is photometric redshift, which is a fancy way of saying we take images through different colored filters and look for the telltale cliff in brightness where the intergalactic fog-neutral hydrogen has eaten the bluest light. That cliff slides redward with distance, so its position hints at redshift. It's quick and powerful, but it's also a little flirty. Dust, oddball stars, and bright emission lines from star-forming regions can dress up as distance and fool you. The gold standard is spectroscopy, where you spread the light out into a rainbow and measure the positions of specific fingerprints like hydrogen's Lyman alpha line or oxygen's O3 lines. Spectroscopy is slower, pickier, and magnificent when it lands a clean measurement. A lot of the early, whoa, big galaxies already? Moments started with photometric guesses, and then began getting spectroscopic confirmations for a subset, which is exactly how you want the court case to proceed. Quick suspicion, slow proof. Even once you're sure a galaxy is genuinely that far, calling it massive isn't just a tape measure trick. It's an inference about how many stars live there. We get that by fitting the galaxy's colors to models of stellar populations, essentially asking, what mix of young and old stars with what metal content would produce this spectrum? The catch is that early galaxies are messy in ways our models still struggle to capture. They can be very young, with stars that are hotter and more massive on average than typical present-day populations. They can be loaded with emission lines bright, narrow features from glowing gas that sneak into the filters and make the galaxy look brighter in certain bands than a star-only model would guess. If you don't account for that, you overestimate the mass. They can have a Balmer break, a step in the spectrum that mimics the signature of an older population, even if what you're really seeing is a cocktail of starlight and nebular glow. They can also be helped by gravitational lensing, where a foreground mass magnifies them. Lens a galaxy and it looks brighter for free. If you don't realize you've been given a magnifying glass, you'll think the galaxy itself is inherently beefier. None of this is hand-waving. It's the day job. Comb through every boring way you might be fooling yourself before you declare that kindergarten is full of fourth graders. At the same time, it would be silly to shrug everything off. There are real surprises in how many bright, early sources we're finding, and that pushes on two parts of our story. The astrophysics of how fast stars can form when the universe is young and metal poor, and the cosmology that sets the overall timetable for how structure clumps. On the astrophysics side, low metallicity astronomy's rude word for not much besides hydrogen and helium changes the rules. With fewer heavy elements to absorb light and help gas cool in fussy, line-by-line ways, cooling pathways shift, fragmentation of gas clouds can change, and the initial mass function, the statistical spread of newborn star masses, might tilt more top-heavy, meaning a larger share of massive, short-lived stars. Massive stars pump out outrageous amounts of ultraviolet light and die quickly as supernova, both of which leave loud fingerprints. Intense emission lines, strong winds, and bursts of energy that shake the gas. If the early universe leaned even slightly toward that top-heavy tilt, you could get more light per unit mass, which makes a galaxy look older or more massive than it really is if you assume today's star statistics. That's not cheating. That's a reminder that we've only ever watched one universe learn to make stars, and we caught it deep into adulthood. The newborn nursery may have played by different house rules. Then there's dust, the eternal party crasher. Tiny grains of carbon and silicates form in the outflows of stars and supernova and love to soak up blue light and re-radiate in the infrared. If an early galaxy is dustier than we expect, its colors shift in ways that can be misread as older or more massive, unless you allow for that. But building dust takes time and supply. Chained stars have to live and die to make it. So there's a tug of war in the modeling between low metallicity, dust-poor assumptions, and the very real fact that even a few early rounds of star formation can seed a surprising amount of dust. That's why people chase follow-up observations at longer wavelengths, trying to catch the faint glow of warm dust. See that glow, and you can add a new line in the ledger. Don't see it, and you start to believe the mass-to-light ratio assumptions a bit more. On the cosmology side, the question is whether the overall schedule left enough time for clumps to grow without an extra nudge. Gravity builds structure from tiny ripples seeded in the early universe. The growth rate depends on how much matter there is to pull, on the expansion rate that fights against the pull, and at very early times, on the exact mix of light, particles, and any exotic fields sloshing around. If you give the early universe a brief, subtle push for a short window, you can slightly change how big those ripples look in the baby photo and the pace at which structures can gather later. That kind of tweak has a name in the rumor mill and a laundry list of ways it could go wrong if it also messes up the baby photo pattern, the polarization signals, or the way galaxies space themselves out at later times. The point isn't to sell you on a fix. It's to explain descent. If the early galaxy counts are robust and stubborn, they make you recheck both the kitchen physics, how gas cools, how stars ignite, how feedback from stars and black holes kicks the gas around, and the building code, how the whole cosmic timeline translates early ripples into present-day clumps. A word about feedback, because it's where a lot of intuition gets wrecked. Gas wants to make stars. Stars then heat and shove that gas. Black holes feed and launch jets, and the whole process runs in a loop. In a small galaxy, one burst of massive star formation can punch holes in the gas reservoir and shut further star-making for a while. In a larger one, the gravity well is deep enough that the gas rains back in. Early on, when densities are higher and everything is more compact, the same punch can have a bigger effect. That means your naive more gas equals more stars instinct can fall on its face if the first generation of stars is too rowdy. On the flip side, some feedback can compress gas and trigger more star formation next door. It's messy, and that mess is why supercomputer simulations that include all the subgrid physics star formation recipes, feedback models, radiation transport are both essential and dangerously tunable. You can make almost any cake if you're allowed to tweak the oven mid-bake. The discipline is to lock the recipes based on local, well-studied galaxies and then ask whether the same recipes reproduce the early statistics without extra knobs. You'll also hear people toss around cosmic variance, which is a polite way to admit the universe is one finite thing, and at early times, we're still looking through relatively small windows. If your survey stares at a patch that happens to sit on a particularly lucky filament, you'll see more bright galaxies than average and start writing hot takes. The cure is boring. Widen the footprint, map multiple patches, and let chance even out. Another quiet gremlin is Eddington bias, where measurement errors in brightness scatter more dim objects up into your bright bin than bright objects down into your dim bin, because there are simply more dim ones. That inflates the bright counts unless you correct for it. None of these caveats ruin the fun. They just keep the adult in the room while we enjoy the toddler chaos of a new data era. If you want to clean, a MIND's eye test for whether the early galaxy hubbub matters for the bigger picture. Tie it to reionization. Turning the cosmic lights back on requires enough ultraviolet photons to escape from young galaxies into the intergalactic medium. Count more bright early galaxies and assuming their light isn't all trapped by local dust and gas, you're closer to having the budget to rayonize the universe on schedule. If, on the other hand, the bright counts settle down and most of the action comes from swarms of faint, hard-to-see galaxies, then the story shifts toward the many fireflies instead of a few flashlights version. Either way, the same machinery that estimates masses and ages also estimates how many ionizing photons leak out. So the early galaxy census isn't just a curiosity. It feeds directly into the question of how and when the fog lifted. What I like about this moment is that it asks us to be bilingual, to speak both the language of careful observation spectra, selection functions, calibration headaches, and the language of physical storytelling cooling, fragmentation, feedback, and the growth of structure, and to let those two languages edit each other. If the early heavyweights slim down as better spectra arrive, that's not a failure, it's the system working. If a subset stays stubbornly overachieving even after every boring correction, that's a clue with teeth. Either way, we end up with a sharper picture of how the first neighborhoods in the universe came online, and that picture plugs back into everything else we've argued about. The expansion rate, the invisible scaffolding, the quiet push that speeds the expansion, and the map on the fridge that started this whole conversation. If you want to know whether the universe is keeping its promises, you don't just measure how fast the room is stretching. You check how lumpy the furniture has become. That's the heart of the growth of structure story, and it's quietly as important as the expansion rate debate. Gravity takes the faint ripples we see in the cosmic baby photo and turns them into a cosmic web of filaments, clusters, and voids. If the ingredients and the rules are exactly what we think, there's a specific pace at which that web should sharpen. Too much clumpiness too soon, and the recipe was too aggressive. Not enough clumpiness, and something's been damping the growth. Astronomers give this clumpiness a scoreboard number with a deeply unromantic name, Sigma 8, written as Sigma G, which is basically how bumpy is the mass distribution when you smooth it on scales of 8 megaparsecs, with a megaparsec being about 3 million light years. Think of it like running your hand over a table with your palm big features you'll feel, tiny crumbs you won't. Sigma G tells you how much your palm notices. Measuring that bumpiness without cheating is an art. One route uses weak gravitational lensing, the barely perceptible way that mass along the line of sight stretches and twists the apparent shapes of distant galaxies. No single galaxy tells you anything. Each one is an individual mess, like trying to judge the wind by watching a single leaf. But stack millions of them across huge patches of sky, map the correlated stretches, and all of a sudden, you're feeling the wind. Those correlated stretches, the cosmic shear turn, into a clean measurement of how much the invisible scaffolding has grown with time. Another route watches how galaxies move in redshift space, with their peculiar motions, little tugs and flows on top of the overall expansion squash and stretch, clustering patterns in a way that lets you read the growth rate directly. A third, more indirect check comes from counting the rarest, fattest galaxy clusters, because their abundance is absurdly sensitive to how quickly the web has sharpened. 3 different microphones, 3 different background noises, and when they sing the same note, you can trust the melody. Here's where the late-night eyebrow goes up. The baby photo, when you feed it through the standard rules and march forward in time, predicts a certain level of present-day clumpiness. The Lensing and Friends measurements sometimes lean a bit lower than that prediction. Like the cosmic web is a touch smoother than the early forecast suggested. Not wildly off. This is not a throw the map out the window moment, but off enough to keep people checking. The math and the plumbing. If you've heard people mutter about an S8 parameter, that's just a neat combination of sigma, G with the average matter density that Lensing likes to measure. The gist is the same, a hint that late-time growth might be a hair suppressed compared to what the early recipe alone would imply. Pair that with the expansion rate mismatch, and you get a very modern kind of headache, because tweaks that fix one can make the other worse if you're not careful. It's like adjusting the oven to save the center of the cake and discovering the edges went dry. Before we go shopping for new physics, it's worth honoring how finicky these measurements are. Weak lensing asks you to measure galaxy shapes at the level where the atmosphere, the telescope optics, and the camera all conspire to fake a signal if you're sloppy. You spend years modeling your point spread function, the way a perfect dot of light blurs through your system, so you don't attribute instrumental smearing to cosmic stretching. You build simulations of fake skies to make sure your pipeline doesn't invent patterns out of noise. You map huge areas because the universe itself is noisy. The polite term is cosmic variance, and any one patch might be a little smoother or lumpier than average by chance. Redshift space distortions have their own gremlins. Galaxies live in messy halos. Survey select galaxies with personalities, and your statistical model has to separate the coherent flows, driven by gravity, from the small-scale jitters inside those halos. Cluster counts suffer from the fact that you never weigh a cluster directly. You infer its mass from proxies like X-ray brightness or the slight dimming of the microwave background as hot electrons. Jiggle each proxy with its own calibration drama. None of this is a reason to give up. It's why the field is careful, and it's why a mild shortfall in growth gets attention only after a lot of plumbing checks. Suppose, after all the unsexy work, the hint persists that the web is a little smoother than the early forecast. There are a few storylines you can reach for without turning the plot into science fiction. One is that something slightly hotter than we assumed has been sloshing around and erasing some small-scale structure. Light, fast particles neutrinos are the classic example. Don't like to clump on small scales because their thermal motions let them skate out of shallow gravity wells. In practice, that means the total mass in those ghost-like particles matters. More mass there, and the web grows a touch more slowly. That's not a wild idea. It's standard physics with a dial you can actually measure. Another storyline is that the same gentle push that accelerates expansion, the dark energy-ish part of the script, might have a tiny time dependence or a whisper of interaction with the invisible, matter that would change the exact growth rate at late times. You don't get that for free. It has to thread the needle, leaving the early baby photo alone, while trimming the late-time clumpiness just enough to match lensing. A third, more prosaic route is that some of our late-time measurements still carry small biases we haven't fully exercised. People groan when they hear that, because it sounds like a cop-out, but history is brutal on this point. A shocking number of tensions dissolve into better calibration. What keeps this particular hint interesting is that different late-time, microphones-independent lensing surveys with different cameras and strategies, different flavors of galaxy clustering, different cluster catalogs have flirted with the same direction of the mismatch, even if not all with the same strength. That repeatability doesn't prove a new chapter. It does raise the stakes on getting the systematics right. It also intersects neatly with the expansion rate drama in a way that keeps theorists honest. If you add a brief dollop of extra energy early on to fix the expansion mismatch, you might accidentally pump up the growth later, unless the dollop fades just so. If you slow late-time growth by fiddling with the push that accelerates expansion, you risk wrecking the distance redshift relation that supernova and galaxy rulers have mapped. The safe path, as always, is to let data from as many independent angles as possible pin down the wiggle room. There's a human piece to this that I wish more people saw. The teams that map weak lensing don't just publish a number and move on. They publish a small novel about how they modeled the atmosphere, how they deconvolved the optics, how they calibrated the shapes with simulations, how they blinded themselves to the final answer until every choice was locked. The teams that measure redshift space distortions write love letters to their fiber positioning systems and their selection functions, because they know that a tiny preference for one kind of galaxy over another can tilt the growth rate. The cluster people argue about mass proxies, like chefs fight over salt. It's fussy, it's slow, and it's exactly why any residual discrepancy, after all that, earns the right to be called intriguing rather than imaginary. If you want an intuitive grip on why a smoother web matters outside the guild, tie it to the story of galaxy histories. A universe where structures grow a touch more slowly late on is a universe where, all else equal, the supply lines for making new stars thin out a bit earlier, and where the biggest galaxy clusters, those ridiculous city-states of the cosmos, are a hair rarer. That doesn't flip the sign on anything. It shades the timeline. It says your cosmic weather app predicted a partly cloudy afternoon, and you got slightly more cloud than sun. You still had your picnic. You just reached for the light jacket. By the end of this class, the responsible attitude is the same one we've carried since the opening booth. Curious, allergic to melodrama, hungry for cross-checks. The early map makes a bold prediction for how rough the cosmic tabletop should feel under your palm today. The late-time surveys run that palm over millions of square degrees and sometimes say, feels a touch smoother. Maybe we'll find the smudge on the palm some tiny bias hiding in our instruments or our assumptions. Maybe we'll find that a small, perfectly legal ingredient more mass and fast, ghost-like particles, a barely time-varying push, a whisper of conversation in the invisible sector brings the feel of the table and the forecast into line. Either way, the test won't be decided by vibes or eloquence. It'll be decided by more sky, better shapes, cleaner spectra, and a pile of independent microphones humming in tune. If this whole story has a detective file with coffee rings on it, it's the one labeled Hubble Constant, which is just the now-ish slope of expansion, written in units of kilometers per second per megaparsec. How many extra kilometer per second of recession you pick up for every cosmic block of roughly 3 million light years. The reason it keeps us up is simple. There are two very careful ways to get it, and they settle a few percent apart in a way that hasn't felt like random noise for years. One path is local and hands-on. You start with geometry. You can trust parallax, the tiny apparent shift in a nearby star's position as Earth orbits the Sun, and you use that to calibrate standard candles. Objects whose true brightness you can predict well enough to turn apparent brightness into distance. Kifide variables, those bright pulsating stars with a rhythm tied to how luminous they are the classic rung because you can see them in galaxies that also host Type Ia supernovae, the big thermonuclear blowouts that serve as distance markers much farther away. Calibrate the candles nearby, step them out to supernova host galaxies, then ride the supernova out into the smooth Hubble flow where local tugs don't matter much, and read the slope. Do this with modern parallax data, obsessive crowding corrections, because Kifides live in busy, star-packed neighborhoods that can make them look brighter than they truly are, and careful color and metallicity adjustments, and you land in the low to mid-70s in kilometer per second, MPC. The other path starts with the universe's baby photo, the faint microwave afterglow from when everything cooled enough for light to travel freely. That pattern encodes the early recipe so tightly that, if you fold in the simplest picture for how the ingredients evolve, you can predict today's slope and get something in the high 60s. Both sides publish uncertainties that sound small. Both have spent years hunting down sneaky biases. The gap survived. Once you zoom in, the local ladder isn't a single rope so much as braided cords that agree where they touch and argue over frayed strands. There's a calibration route that likes the tip of the red, giant branch, an evolutionary moment when aging stars hit a near-standard brightness right before changing character. Those stars tend to sit in calmer, less crowded parts of galaxies than Kifides, and the method's quirks are different. When that tip is used to anchor the supernova distances, the final slope often lands a bit lower than the pure Kifide anchor, nudging toward the baby photo value without quite shaking its hand. There are Maser's natural microwave lasers from water molecules, whipping around the centers of a few lucky galaxies that trace orbits you can clock and model with geometry alone. A kind of cosmic yardstick that bypasses candles entirely. Fold those in, and you get another independent check that usually sits in between the two headline values, depending on which galaxies and which models you allow. And there's a method called surface brightness fluctuations, which takes advantage of the graininess in a galaxy's starlight. Closer galaxies look noisier because individual bright stars contribute more to the texture, and you can turn that noise into a distance if you've calibrated it nearby. Each of these is a little fussy, each has a personality, and the grown-up move is to cross-calibrate all of them against the same geometric anchors. So the fight is about physics, not about who miscounted the forks. The supernova rung itself has drama that isn't scandal, just craft. Type Ia events are standardizable, not perfectly standard. You correct their peak brightness using how their light curves rise and fade in a color term that tries to disentangle dust from intrinsic tints. You also have to admit that supernovae don't go off in random places. Their host galaxies have different masses and star-forming habits, and those environments correlate with tiny shifts in the calibrated brightness if you ignore them. It's not enough to stack distant explosions and call it a day. You need a clean bridge between the nearby set you calibrated and the far set you use to read the slope. People build that bridge with a kind of grumpy thoroughness that ruins dinner parties and saves numbers. They revisit 0 points for photometry. They model how much light leaks between pixels. They simulate the selection effect that brighter things are easier to discover and reweight the sample to compensate. They argue about whether dust in other galaxies behaves like dust in the Milky Way, and they blind their analyzes so they can't subconsciously steer the result toward a beloved answer. After all that, the local slope stays high. You might wonder whether the very neighborhood we live in could tilt the readout. If the nearby universe has a mild under or overdensity, think of it as a slightly roomier or slightly more crowded patch. Local galaxies could have peculiar motions on top of the general expansion that bias a slope measured too close to home. That's why latter teams push their supernova sample deep enough that those local tugs average out, and why they model flows in the nearby web with maps of galaxy density. You still want a guardrail here, because the safest place to read the slope is where those extra motions are small compared to the overall recession. But it's not a magic delete key for the tension. The bias from local flows would have to conspire across multiple independent samples in the same direction with almost cartoonish persistence. It's not impossible. It's just not the bet most people would place after the last few rounds of checking. On the far side path, the baby photo isn't the only voice on team high 60s. The universe carved a ruler into the large-scale pattern of galaxies. The faint preference for a certain separation that comes from sound waves rattling the early plasma. Measure that ruler at different redshifts, and you get a clean handle on how distances scale with time. Combine those measurements with what we know about the average matter content, and you tend to land close to the baby photo prediction. There are also time delay lenses, the dramatic systems where a single background quasar appears in multiple images because a massive galaxy is bending its light. Those light paths are different lengths, so when the quasar flickers, you see the echoes at different times, and the size of that delay depends on the cosmic distances involved. If you can model the lensing mass and the clutter along the line of sight well enough, you get a slope that, interestingly, often favors the higher, ladder-like value, although the modeling baggage is heavier and the sample is small. That split result is either a clue or a headache, depending on how much coffee you've had. What would it take, in principle, to bring the two camps together without accusing anyone's camera of lying? One idea on the menu is that the early universe had a brief extra dollop of energy, call it an early time puff, that changes how big the baby photo ripples look, nudging the inferred slope upward when you translate early measurements into today's units. The puff has to switch on and off without mangling the rest of the exquisite pattern, and it has to leave later. Late time measurements of growth and distances mostly unchanged. Another idea is that the invisible sector dark matter and whatever drives the acceleration has a whisper of interaction that shifts the bridge between early and late without wrecking either end. Those are not free lunches. They pay rent by making predictions you can test as data improve. The more boring possibility is still alive, and boring for a reason. Small, stubborn calibration quirks in one or more ladder rungs, or in one or more assumptions that translate the baby photo into today's slope. History is merciless about this. Calibration has killed more revolutions than theory ever has. A brand new referee is walking into the bar. Oh, and that's gravitational wave standard sirens. When two neutron stars spiral together, the ripples they send through spacetime carry an absolute loudness that lets you read distance without candles or rulers. Catch light from the same events, so you can get a redshift from the host galaxy, and you've built a distance redshift point from first principles. One siren isn't decisive. A chorus will be. The early handful are messy and far apart on the sky, so their host IDs are shaky. But as detectors get more sensitive and the catalog grows, they'll weigh in with a tone neither camp can ignore. There's also a patient experiment you can think of as a cosmic breath test: redshift drift. If you stare at precise spectral lines in faraway objects for enough years, the ongoing expansion should nudge those lines by a tiny amount in real time. That's the kind of measurement that needs absurd stability and the patience of a saint. But if it lands, it doesn't care about ladders or baby photos. It reads the expansion changing under our feet. If you asked me, off the record with the neon humming, where the smart money sits, I'd say the skeleton of both approaches holds. The local ladder will keep tightening the screws with better parallax, cleaner Kithide fields, and more galaxies where multiple anchors cross in the same system. The baby photo plus ruler path will keep shaving systematic fuzz with better maps of galaxies and improved modeling of foreground junk. Time delay lenses will bulk up their samples with sharper mass reconstructions. Sirens will grow from duet to choir. The gap will either shrink into we finally found that last percent hiding in the attic, or refuse to budge and force us to install that extra plank in the early recipe. Either outcome is a win. One cleans the glass. The other gives us a new pane with a view we didn't have before. Dim the lights a little, and it's almost poetic. We learn to measure a slope that describes how all of space stretches. And now we're arguing, with numbers at the percent level, about exactly how steep that slope is. The argument is not a crisis. It's a luxury you only get when your instruments and your discipline have gotten frighteningly good. If the universe is trolling us here, it's doing it gently, handing us a puzzle whose solution will either be a beautifully mundane calibration or a beautifully small surprise in the early time playbook. Either way, the next few years have the feel of a lock clicking. If you want to talk about where we were wrong in the most interesting way, you have to walk right up to the opening act. The idea that the universe did a wild sprint in its first split second. The friendly name is inflation. Picture the cosmos, not as a fireball exploding into emptiness, but as all of space itself getting yanked wider by an almost absurd, ultra-brief growth spurt, so fast that regions that were once cozy, neighbors got flung far apart before light could ever gossip between them. Why go there? Because without that sprint, you run into two riddle of the cosmos headaches. First is the horizon problem. Different patches of the sky, separated by such ridiculous distances that they should never have shared information, look weirdly the same temperature, like two strangers showing up to a party in matching jackets. The second is the flatness problem. On the biggest scales, the geometry of space behaves like a perfectly level table, when tiny tilts should have grown into obvious slopes over billions of years. Inflation is the cheat code that levels the table and lets the jackets match. The sprint stretches any wrinkles almost out of existence and makes the visible patch of the universe look uniform and flat. The way a balloon looks smooth to an ant, even if the balloon itself is lumpy. The sales pitch doesn't end there. Inflation doesn't just fix old problems. It gives you a way to see the structure we see today. During that microscopic sprint, tiny quantum jitters, the kind of fluctuations that always hum in the background at the smallest scales, get stretched to cosmic size and frozen in. Those become the faint overdensities that gravity later fattens into galaxies and clusters. It's an outrageous idea that somehow manages to be both bold and practical, like admitting you used a shortcut and then showing your receipts. The receipts are the tiny freckles in the baby picture of the universe, the pattern of slightly hotter and cooler spots in the ancient glow, which line up with the stretched jitter story in both size and overall tilt. Tilt here just means the power in those fluctuations is a hair stronger on large scales than small, which is exactly what a big family of inflation models predicts. You can explain this at a bar with a cocktail napkin. Blow up a speckled pattern fast enough, you get a speckle size, a faint preference for one scale over another, and a way to timestamp the sprint. But here's the bit that keeps cosmologists honest. Once you start asking what precisely did the sprint, what field, what mechanism, what set of knobs you step from postcard physics into a junk drawer, there isn't one inflation. There are many flavors in the cookbook. Some have the sprint powered by a single field rolling slowly down an energy hill. Others have multiple fields trading energy like jugglers. Others let the sprint end with a messy event called reheating, where the field's energy dumps into a hot soup of particles that becomes the young universe we actually recognize. The moment you allow many recipes, you're in danger of explaining everything and therefore nothing. That's why people spend so much time chasing specific signatures that would narrow the menu. One big signature would be primordial gravitational waves, the ripples in spacetime. Itself launched during the sprint, which would leave a particular swirl pattern in the polarization of the ancient glow. Detect that swirl cleanly at the right levels, and you've basically heard the heartbeat of the opening act. People have built exquisitely sensitive instruments to listen for it. They've also tripped over a swamp of foregrounds dust in our own galaxy that can mimic the swirl. And over the years, the "we heard something" noises have been patiently walked back as the foreground modeling got better. That's not defeat. That's the method. You keep cleaning the room until the only music left is either the universe or the hum of your own equipment. There's a second, more subtle signature people hunt called non-Gaussianity. It's a mouthful, so here's the bar version. If the seeds of structure were just stretched jitters, their statistical pattern should be almost, but not perfectly, like rolling a massive number of fair dice, very simple, very nearly Gaussian. Certain fancy models add little interactions that skew that dice roll in a recognizable way. We've looked hard. So far the sky keeps saying, if there's skew, it's tiny. That gently slams doors on Baroque versions of the sprint without killing the whole idea. The same goes for sharp features, little wiggles in the pattern that would hint at a sudden change during the sprint. A few analyses have flirted with hints. Nothing has walked into the room wearing a name tag yet. Every non-detection isn't a bummer. It's a haircut for theory space. The cosmos is telling us it prefers the versions of the story that are smooth, simple, and not too fussy. If this all sounds like inflation is the only game in town, that's not true. And this is where the maybe we were wrong spirit gets fun. There are alternatives that try to solve the same party trick problems without a sprint. Some tell a bounce story. Instead of beginning in a hot, dense state that then sprinted, the universe was contracting under its own weight, smoothed itself out during the contraction, and then bounced into expansion. Others tell a slow contract, then gentle roll story with different physics shaping the initial conditions. These are elegant in their own way because they try to dodge the parts of inflation that feel tuned or vague. But they pay rent in a different currency. They have to reproduce the same baby picture freckles, the same near flatness, The same remarkably uniform jacket colors across the sky, and they have to do it while not inventing side effects we don't see, like defects or dramatic distortions. It's not impossible. It's just a high bar, and so far the Sprint has kept the lead because it hits the checkboxes with fewer moving parts. That doesn't mean it's the final word. It means it's the working word. There's also the awkward cousin at every family dinner, the multiverse angle. Some inflation models end not with the Sprint switching off everywhere at once, but with pockets where it stops, while elsewhere it keeps going, bubbling off new regions with slightly different settings. That picture can make your head hurt in two ways. One, it tempts you to shrug and say anything can happen somewhere, which is science poison if you're not careful. Two, it raises hard questions about what it even means to make predictions when you can't sample the whole ensemble of pockets. The responsible middle ground is to remember why this idea shows up at all. It falls out of certain Sprint recipes, whether you like it or not, and to focus on signatures we can test in our one observable patch. If tomorrow someone measures a clean primordial swirl in the ancient light, that will jack up the odds for models that tend to produce big gravitational waves and shrink the space for many alternatives, with or without extra universes riding shotgun. Meanwhile, the end of the Sprint, the handoff to the hot, dense state we usually start our story with, is its own science project. That reheating phase determines how the first particles show up, how quickly the soup reaches thermal equilibrium, and whether any exotic relics survive to leave fingerprints we could see today. It's not just esoteric bookkeeping. It nudges the timeline that connects the baby photo to later observables. And tiny nudges matter when the rest of your story is precise. If you ever wondered how cosmologists can argue for hours about something that lasted far less than a blink, this is it. The Sprint is like a drummer's ghost, note barely there, shaping the groove. Get it wrong, and everything that comes after feels slightly offbeat. So where does that leave the "were we wrong" question? The cleanest answer is that the broad sketch of an early smoothing mechanism that also seeds structure has aged well, while our first-pass confidence in specific, pretty models has been steadily sanded down by data. We thought the swirl signature might be right around the corner. It wasn't. We thought certain elaborate versions might survive contact with the sky. They didn't. We thought the tilt might be exactly flat. It's a hair off. Each revision wasn't a defeat. It was a nudge toward a plainer, tighter story. And at every step, the way we learned we were wrong was the best part. Cross-checks between the ancient glow, galaxy maps, lensing, and the growth of clumpiness, all humming to the same key when the idea was good, and going sour when the idea was overseasoned. If you and I step back from the whiteboard and breathe, the honest bar chat summary is simple. We probably did live through a tiny, ferocious smoothing and stretching that planted the seeds of everything. The universe has been polite enough to keep confirming the general outline, and impolite enough to refuse our favorite flourishes. That's perfect. It means there's still a real hunt on for the drummer's ghost note gravitational waves from the opening act. A small skew in the statistics, a crisp feature that says, this happened, not that. It means the alternatives haven't been banished. They've been given a standard to beat. And it means the next upgrade won't arrive as a tweak. It'll arrive as a plot that got cleaner, a foreground that got modeled better, a detection that survived every boring test we could throw at it. There's a special kind of whiplash you get the first time you realize the universe already had monster black holes when it was barely out of diapers. I'm not talking about the cute stellar ones that weigh like a few suns. I mean the supermassive kind, millions to billions of solar masses, running bright quasar lighthouses when the cosmos was a few 100 million years old. You stare at those early beacons, and the first instinct is to check the date on the photo. If structure was still stretching and settling, how did anything have time to eat that much and glow that loud? That's the puzzle. The clock looks tight, the engines look huge, and yet the sky is not shy about showing them off. To get your head around it, you need two pieces. One is the idea of a seed, a starting black hole, before the bulking up begins. The other is the feeding rule. The classic seed everyone learns about comes from the first generation of stars, which astronomers call population 3. Those were metal-free stars, born in a universe with only hydrogen and helium. And without the heavy elements that help gas cool, some of them likely got truly massive. Massive stars live fast and die hard, collapsing into black holes a few tens to maybe a couple of 100 times the sun's mass. That's a fine seed if you have time to let it sit in a buffet. The problem is, the buffet closes early in the young universe. If you try to grow a black hole from a POP3 remnant to a billion suns using the normal feeding rules, you end up grumbling about the clock. That feeding rule hides behind a phrase that's scarier than it needs to be: the Eddington limit. It's just the tug of war between gravity pulling gas in and radiation pushing it out. As gas falls in and heats up, it shines. That outgoing light pushes on the incoming gas. If the light pressure gets too strong, it chokes the inflow. There's a comfortable balance where the hole can keep eating at a steady, exponential pace. People love to explain it with a bank account. And honestly, it works. Eat at the Eddington rate, and your mass compounds at a fixed percentage every few million years. With enough time, even a small seed becomes a big account. With not enough time, you need a higher interest rate or a bigger initial deposit. That's why the conversation keeps circling two escape hatches. One is bigger seeds. Instead of starting from the corpse of a single massive star, maybe some early patches of gas skipped star-making altogether and collapsed straight into a black hole, 100,000 to a million suns in one go. That's called direct collapse, and getting it to happen is like trying to bake a cake without it breaking into smaller pieces. You need the gas to stay hot enough and unfragmented long enough to fall in as one big, sulky blob, and you need to prevent early starlight from cooling it into little clumps. There are ways to imagine that happening fierce ultraviolet light from a nearby starburst, for example, can shut down the molecule that's too good at cooling. But the details are fussy, and the neighborhoods that allow it might be rare. Rare, though, is fine if they plant the seeds for the few early quasars we actually see. The other hatch is to let the black holes cheat on the feeding rule for short stretches. Super Eddington sounds illegal. It just means geometry and mess help you slip more gas in than the neat textbook would allow. If gas funnels in a thick, clumpy disk, a lot of the radiation can leak out along paths that don't blast the incoming material, so the effective pushback is weaker and the inflow can be higher. You don't get to do that forever without blowing your cover, but a few supercharged growth spurts early on could bridge the gap between plausible seeds and the skyscrapers we see lit up as quasars. The signatures of that kind of feeding are not abstract. The light near the black hole gets a particular blue tilted shape. Winds become rowdy, and the neighborhoods look turbulent. Catch enough of those traits in a young system, and you start believing the fast bulk story. Once you allow either bigger seeds or naughty feeding, or a bit of both, you can start sketching a believable path. You still need luck. Black holes don't live in isolation. They sit at the centers of galaxies, and galaxies merge. Every time two galaxies dance together, their central black holes begin a drawn-out tango that can end in a merger. If they fling enough stars and gas around to lose orbital energy, merge two black holes, and you don't just add masses. You can also launch a flash of gravitational waves, a ripple in spacetime that carries away energy and momentum. If the waveform is asymmetric, the remnant can get a kick, which in extreme cases could even shove it out of the center for a while. Most of the time it'll sink back in and keep eating, but it makes the growth path messy and personal for each object. Somewhere in all that mess lies the true story for each early giant. Some combination of a decent head start, a few feast days, and a social life that involved mergers instead of solitude. When astronomers talk about seeing these black holes at early times, what they actually see is the gas daring to fall in. That gas heats up and glows across the spectrum, from ultraviolet and optical light to X-rays. In the optical, you get broad emission lines blurry, features in the spectrum that come from gas whipping around at thousands of kilometers per second near the hole. The width of those lines, combined with the brightness of the surrounding luminous fog, lets you estimate the mass of the black hole with a method that has a lot of caveats, but works shockingly well in large samples. At higher energies, you get X-rays from the hottest parts of the inflow. In the infrared, you see the dusty cocoon that the central engine has heated. Tie those together, and you can say, with a straight face, that you're clocking a black hole's diet at a time when the universe hadn't yet built most of its galaxies. There's a lovely feedback loop here with galaxy formation. A hungry black hole doesn't just eat, it also spits. As matter swirls in, magnetic fields and heat launch winds and jets that can travel thousands of light years, jostling or even ejecting the very gas the galaxy would otherwise use to make stars. If the galaxy is small, those tantrums can shut down star formation for a while. If it's big, the gas might cool and rain back in, setting up cycles of feast and famine. That give and take helps explain why the mass of a central black hole correlates with the properties of its host galaxy's bulge, even though one is subatomic compared to the other on cosmic scales. A black hole is a tiny CEO with an outsized bonus plan, and the neighborhood learns to live with its moods. Every time we push deeper, we add a new messenger. Light has carried most of the conversation so far, but the next decade gives us more ripples. Gravitational waves from massive black hole mergers would be a direct census of how often these giants found each other and how fast they grew by union versus diet. Catching a merger at high redshift would be like finding a marriage license filed in a frontier town. It tells you the social graph was dense early, not just the pantry. There's also the hope of catching the very moment a direct collapse seed forms by its peculiar light signature, or at least boxing the idea in by showing that certain neighborhoods at early times were hostile to normal star formation in a way that would favor collapse. Even if those smoking guns stay elusive, the indirect constraints tighten every time we measure a black hole's mass at a redshift that makes your eyebrows go up. A few more eyebrow raisers, and the gap between interesting, and okay, we need the big seeds or the rule bending snaps shut. I like this chapter because it refuses to let you be cynical. On paper, it's a math problem about exponential growth and short calendars. In the sky, it's drama. Gravity building funnels, radiation pushing back, gas threading the needle, galaxies bumping into each other, black holes marrying, neighborhoods lighting up like neon signs after rain. If we were wildly wrong anywhere, it was in assuming the early universe would be timid. It wasn't. It built engines fast, it fed them creatively, and it left us just enough light to read the receipts. Whether the ultimate fix is start bigger, eat faster for a bit, or do both and dance, the point is the same. The cosmos had more hustle in the first billion years than our first drafts gave it credit for, and that hustle echoes in every massive, quiet black hole dozing at the center of a modern galaxy. There's one chapter in this whole saga that feels less like astronomy and more like a riddle someone left on a napkin. Why is the push that speeds up the universe so tiny, so steady, and so perfectly timed to matter right now? When people say dark energy, the most vanilla translation is energy of empty space, also called vacuum energy. That sounds mystical, and it's really just saying the vacuum isn't a blank zero. It has a small, constant energy density per cubic meter. How small? Take the mass of a proton, about 1.7 times 10 squared, why? Kilograms, and imagine 4 of them spread in each cubic meter of space. That's the ballpark. You could stare at a 1 meter cube all day and never notice. And yet, when you smear that whisper across billions of light years, it wins the tug of war and nudges the expansion to accelerate. The number is small enough to feel like a practical joke and big enough to reshape the cosmic timeline. That's the first itch. The second itch is timing. For most of cosmic history, matter, both ordinary atoms and the invisible scaffolding, was doing the heavy lifting. As the universe expands, matter thins out because the same amount of stuff occupies more room. Double the size, 1/8 the density. Vacuum energy doesn't do that. If it really is a constant energy per cubic meter, doubling the size just gives you more cubic meters, not less energy per cube. That means there's a crossover era when the steady background hum overtakes the thinning matter and starts to call the shots. By a wonderfully annoying coincidence, that crossover turns out to be roughly now on the cosmic clock, give or take a few billion years. People call it the coincidence problem with a straight face because, ooh, really? Doesn't look good in a paper. If the number were 10 times bigger, acceleration would have kicked in so early that gravity wouldn't have had time to grow the gorgeous web of galaxies we see. 10 times smaller in acceleration would still be in the waiting room. We'd be coasting. Instead, we're living right at the hinge. You don't need equations to feel why theorists find that weird. Then there's the elephant in the back room. If you ask quantum field theory, a very successful framework that predicts, say, the magnetic moment of the electron to insane accuracy, how much energy empty space should have. You don't get 4 protons per cubic meter. You get a number so hilariously huge that calling the mismatch a lot is like calling a supernova a spark. Depending on how high in energy you're willing to trust the theory, the naive vacuum energy prediction overshoots the observed value by factors that get written with more zeros than anyone wants to count. People joke it's the worst prediction in physics, not because the math is sloppy, but because nothing obvious explains how the vacuum energy from all those quantum fields cancels down to the tiny sliver we actually infer without also wrecking the rest of physics. In a bar conversation, you can say it this way: our best calculator insists the background hum should be deafening. The sky says it's a whisper, and we don't know who turned the volume knob down without touching anything else. One way to dodge both the timing and the volume knob is to say the push isn't a fixed property of space at all. It's a field that slowly changes in time, a dynamical energy, nicknamed quintessence. You can picture it like a ball rolling so lazily down an energy landscape that for now, it looks almost constant. Because it evolves, it can in principle be small without miraculous cancellations. And because it evolves, you can try to tune its pace so it becomes important only recently. The price of that escape hatch is that you've added moving parts. Moving parts leave tracks. A truly constant vacuum energy makes distances scale with redshift in a very specific way and slows the growth of cosmic structure in a very specific way. A slowly changing field tweaks those patterns. With big enough, clean enough surveys, better supernova catalogs, sharper galaxy ruler maps, more precise weak lensing measurements, you can check whether the cosmic push is really constant or drifting a little. So far, the data have been maddeningly polite to the constant story. If there's drift, it's small. That doesn't kill the idea. It shrinks its playground. Another way around the napkin riddle is to say, maybe we shouldn't be talking about a push at all. Maybe we're misreading gravity on very large scales. General relativity is the rule book we've used for a century, and it's been absurdly successful from the solar system to black hole shadows. But it's a rule book we've tested only in certain regimes. Could gravity look a hair different across billions of light years, in a way that mimics a cosmic push without adding a new energy component? The allure is obvious. Keep the vacuum empty. Change the rule. The trap is equally obvious. Any change has to tiptoe through the minefield of existing tests. Locally, in labs and around planets, gravity looks like Einstein wrote it. Any extra fields you add to tweak large scales must hide themselves in high-density environments, a trick called screening. Globally, the same change that speeds up the expansion also changes how structures grow. If you suppress growth too much or in the wrong pattern, lensing surveys will catch you. The community has spent years building consistency tests that ask, point blank, does the gravity that bends light match the gravity that tugs on matter? So far, the universe has been conservative. No smoking gun deviations, just a lot of tightening nooses around the wiggle room. There's a more philosophical card on the table that makes some people twitch and others nod. Maybe we live in a universe where certain numbers like the vacuum energy aren't set by deep necessity, but by selection. If there are many possible cosmic patches with different settings, then most of them won't grow galaxies or chemistry, or people because the push is too big or the clock runs weird. We, by obvious selection bias, find ourselves in a patch where the numbers allow galaxies and chemistry and coffee. That logic is not an explanation in the usual predictive sense. It's a story about why we shouldn't be surprised by being in a just right patch if many patches exist. Whether you find that satisfying depends on your temperament. The only responsible way to talk about it, in my view, is as a reminder that our intuition about natural values may be a poor guide, and as a prompt to look for independent signatures of the broader picture, like telltale patterns from an ultra-early sprint that often goes hand in hand with those multiverse-flavored models. If the testable piece shows up, say, a clear swirl pattern in the ancient light from primordial gravitational waves, that doesn't prove selection, but it shifts the odds about which family of models we take seriously. There are also attempts to explain late-time acceleration with the structure of the universe rather than new ingredients or new gravity. The idea, called back reaction in this context, says that once you stop pretending the cosmos is perfectly smooth and you average over a real, lumpy web, the leftover effects of lumpiness might add up to something that looks like acceleration. It's a seductive thought because it turns a weird new thing into a bookkeeping of old things. The catch is that teams have done the hard work in many different ways, exact toy models you can solve, numerical averages over realistic lumpy universes, and the result has consistently been that the effect is too small, or it points in the wrong direction, to explain the observed acceleration by itself. That verdict isn't based on taste. It's based on writing the equations in full instead of waving hands. The clouds in the coffee make patterns. They don't turn coasting into speeding up at the percent levels we measure. What would count as a real crack in the napkin riddle? A confident sign that the push changes with time would do it. A clean drift nailed by multiple distance probes and growth rate measurements that all point in the same direction. A lab detection of a new ultralight field that couples to normal matter, just enough to reveal itself, and has properties that match the cosmic drift would be revolution grade. A verified deviation in the light-bending gravity versus matter-tugging gravity comparison, mapped across a range of scales and redshifts, would put modified gravity on the podium. Or, in a different direction, a deep theoretical mechanism that cancels the enormous quantum vacuum contributions down to the tiny, observed value in a way. That plays nice with particle physics and survives contact with the rest of the sky would earn champagne forever. You can feel from the way I'm stacking the words how tall that order is. But tall isn't impossible. It's just a way of saying the next move has to survive a lot more than a good headline. In the meantime, we do the practical thing. Keep asking whether the push looks exactly constant or a hair off, and keep tying that question to independent messengers. The constellation of supernova distances, galaxy ruler measurements, weak lensing maps, and the ancient glows lensing and polarization all pull on different seams. Gravitational wave standard sirens are joining the party with a voice that doesn't care about candles or rulers. Radio maps of neutral hydrogen, the 21-centimeter whisper, promise to chart enormous volumes of space across time, giving us yet another way to see whether the expansion history bends exactly like a constant push would make it bend. It's not glamorous to say we're tightening the net, but that's the honest description. The net tightens quietly for a long time, and then suddenly you realize there's only one fish that fits. I like ending this lap with a human thought. Sometimes being wrong isn't discovering a spectacular new thing. Sometimes it's noticing that your gut for what's natural has been unhelpful. And your job is to trade gut for measurement. The vacuum energy riddle is tailor-made for that trade. The number on the napkin looks absurdly small if you stare at it in units built for atoms and labs. It looks perfectly ordinary when you judge it by the sky it shapes. We'll keep pushing both sides, build theories that don't require miracles, and build instruments that don't forgive sloppiness. And whichever side gives first will feel like the universe winking and saying, "Took you long enough." If there's a secret engine under everything we've been talking about, it's not a telescope or a theory. It's the unglamorous craft of not fooling ourselves. Cosmology only looks like magic from a distance. Up close, it's closer to running a kitchen that never closes. You're tasting broth every 5 minutes, adjusting the flame, throwing out a batch when the salt got weird, and keeping notes so future you remembers what weird looked like. People hear words like bias and think politics. In this room, bias is any tiny shove that nudges a number without owning up to it. The whole game is to spot the shoves before they masquerade as discoveries. Start with the mundane monster everyone underestimates: the instrument. A camera on a mountaintop isn't a window, it's a personality. The optics smear starlight. A little astronomers call that smear the point spread function, and that smear changes with temperature, wind, where you're pointing, even how hard the telescope breathed last hour. If you're trying to measure the barely there stretching of galaxy images caused by gravity bending light across billions of light years, any unmodeled smear turns into a fake signal. So people build a model of the smear that updates every few minutes. They pepper the field with bright stars to sense how the optics are behaving, and they test their measuring code on fake skies where the correct answer is known. You can feel the paranoia in the best teams. They blind their own analysis. Blinding sounds dramatic, and it's simple: hide the final answer behind a digital curtain until every choice about cleaning and modeling is locked. Only then do you peak. It's a social hack against human nature, because humans are brilliant at leaning toward the number they wanted to see. The same humility applies to surveys that live in space, which sounds like freedom from weather and comes with its own gremlins. Detectors age. Pixels don't respond equally. Stray light from a bright star off the edge of the field can bathe your image in a soft glow that looks, in the wrong light, like the universe developed a new feature. The cure is repetition and cross-calibration. You watch the same patch at different wavelengths. You compare one instrument's truth to another's, and you map every boring artifact you can think of so the interesting leftovers have a chance to be real. It's housekeeping as method, and when it's done well, it is wildly beautiful. You run a null test, which is a fancy way of saying, look where there should be no signal. If you see one, you've caught your own hand in the cookie jar. Distance work, the candles and rulers we leaned on earlier, has its own quiet traps, and the same, fix, measure the unsexy things well. Kified variables, the pulsing stars that help set the lower rungs of the ladder, live in bright, crowded neighborhoods. If light from their neighbors leaks into your measurement, they look a hair brighter, and brighter means closer, and closer means the final expansion rate creeps upward. So people resolve those fields more sharply. They correct for crowding. They worry about how metal-rich or metal-poor the stars are, because that nudges the pulsation brightness link. And they insist on geometric anchors, parallax distances measured in parsecs, with a parsec being the distance at which Earth's orbit would make a star shift by 1 arcsecond across the sky. That don't care about astrophysical mood swings. That insistence on geometry is not snobbery. It's the spine the rest of the ladder hangs from. You can feel the discipline in the way results get reported, not just a number, but a number with plus or minus, and a paragraph about what lives inside that plus or minus. Galaxy maps and their standard ruler the faint preference for a certain separation, imprinted by early sound waves, teach a different flavor of humility. It's easy to forget that you never observe the universe. You observe a sample, and samples have personalities. A patch of sky might sit on a filament that's a little richer than average. Your catalog might prefer galaxies with a certain color because your selection method fell in love with them. Your redshift measurements, those color shifts that track distance, might be noisier in one season than another because the instrument was having a week. All of that rolls into what people call the selection function, which is a jargon way of admitting your survey doesn't see all galaxies with equal enthusiasm. The way out is to model the enthusiasm and weigh the galaxies accordingly, and then to ask whether a different independent survey with different enthusiasms and different mistakes lands on the same ruler length. When they do, you trust the ruler. When they don't, you go back to the kitchen. Even the cosmic baby photo, which feels like a gift from the universe itself, is booby-trapped with foregrounds. Our own galaxy is not a polite roommate. Its dust grains glow and polarize light at microwave wavelengths, and the magnetic fields thread that glow into patterns that, to a hurried eye, can look a lot like the subtle swirl one would hope to see from primordial gravitational waves. You don't fix that with optimism. You fix it by observing at multiple microwave colors, because the dust spectrum and the ancient afterglow have different tints. You fix it by building sky maps where the foregrounds are the thing you care about and subtracting them with the kind of patience, usually reserved for detangling necklaces. The first time a teen thought they had heard the universe's opening ripple in the polarization pattern, it was dust doing a convincing imitation. Painful? Absolutely. A failure? Not at all. It was the method, ruthless and healthy, kicking the romance out of the room and asking for better evidence. The flip side of all this vigilance is joy, when independent roots agree. It's hard to overstate what a mood lifter it is, when a weak lensing measurement of how quickly cosmic structure has grown echoes what you inferred from how galaxies cluster, or when a time delay lends those systems where a quasar flickers, and you watch the echoes arrive along different light paths gives a distance that lines up with the ladder you built from pulsating stars and supernova. Agreement doesn't make the bias problem go away. It tells you the biases are, at least for now, not running the show. Disagreement is not a scandal either. It's a do list. A Hubble constant skirmish lives here. Careful teams, different tools, different bad habits, converging toward an answer and refusing to shake hands by a few percent. That stalemate doesn't make cosmology fragile. It makes it alive. One reason we can be brave about tensions is that new messengers keep walking in. Light has been the main gossip, but gravitational waves, those ripples in space-time from colliding compact objects, are starting to serve as standard sirens, distance markers that don't care about how bright something looks, because the loudness of the wave itself encodes how far it traveled. If you can also catch some light from the merger and thus get a redshift from the host galaxy, you've built a point on the expansion curve that sidesteps the usual candle arguments. We don't have a choir yet. We have a handful of soloists and the promise of more. There's also the quiet, patient idea of redshift drift, where you stare at razor-thin spectral lines for years and watch the expansion change those lines by a tiny amount in real time. It's a test that feels like measuring the growth of a tree by listening for the creak of the wood, and it comes with the same requirement for absurd stability. If it lands, it won't ask for anyone's permission. It will simply report what the universe is doing this decade. Radio astronomy is sharpening a different knife by chasing the 21-centimeter whisper from neutral hydrogen across vast swaths of time. Because that line shows up everywhere, there's diffuse hydrogen. It promises a three-dimensional map of the cosmic web as it woke up, reionized, and matured. The challenge is that human radio noise and our own atmosphere are hooligans, and the cosmic signal is the shy kid at the party. But shy kids talk if you give them space. A clean map of that whisper across redshifts would let us track when and where the first neighborhoods lit up and would. Hand us a new ruler to check the expansion history that doesn't care about supernova quirks or galaxy selection. The theme here repeats. Different microphones, different flaws, same song if the song is real. Behind all of this is a culture choice that cosmology stole from particle physics and made its own. Publish your pipelines, share your data when you can, and welcome independent reanalyses that might make your number move in the 5th decimal place. That last bit sounds petty and is the opposite. When numbers are precise, the action lives in the 5th decimal. The first time you watch a reanalysis nudge a result and make 2 feuding measurements move closer, you develop a taste for the kind of humility that keeps fields healthy. It's not self-abuse, it's pride in the right thing. The prize isn't getting the headline first. The prize is getting the story to hold up when someone else reads it cold. So if you ask me what being wrong looks like on an average Tuesday in this field, it's not a dramatic retraction or a confession that we misread the sky. It's smaller and sturdier. It's realizing your background model let a sliver of scattered light sneak through and shaving a % off your signal. It's noticing your galaxy selection lean toward a color that sings louder in your instrument and adjusting the weights. It's upgrading your distance anchor because the new parallax map has half the uncertainty. It's 3 teams who would love to be right for different reasons, deciding to blind their work in the same way, just to make sure no one's hand was on the scale. That unglamorous discipline is why the big story survives the bruises. The universe expands. The ancient glow remembers. Invisible scaffolding shapes where the light lives. A gentle push bends the late-time arc. Inside that frame, the arguments are not a weakness. They're the gears that make the frame worth trusting. If you want one character that keeps sneaking into every subplot we've told, it's the neutrino, the ghost particle that barely notices you exist, and yet helps decide how lumpy the universe gets. For decades, textbooks treated neutrinos like massless afterthoughts, little bookkeeping particles that ferry energy away from nuclear reactions and go home. Then experiments caught them swapping identities in flight neutrino oscillations, which only happens if they have mass, even if it's tiny. That single twist yanked them from the footnotes into the cast list, and cosmology quietly smiled because the sky had been sensitive to their mischief all along. When you hear an astronomer say, "some of the neutrino masses," they're talking about adding up the masses of the 3 known flavors and asking how heavy the whole family is in total. The unit is the electron volt, written EV, which is a ridiculous energy unit for everyday life and a natural one for particles. The masses here are fractions of an EV, featherweight by any human metaphor, and still heavy enough, in cosmic terms, to leave fingerprints. The trick is that neutrinos are born fast. In the young universe, when everything was hot and crowded, they flew around at essentially the speed limit, not caring about clumps. Even as space expanded and they cooled, their thermal motion kept them zippy for a long time. That means they refused to sit in the shallow gravitational wells that ordinary matter and invisible scaffolding were trying to deepen. Give a region a little overdensity, and most matter will help it grow. Neutrinos, if they're still fast compared to the depth of the well, skate right through. The net effect is a gentle brake on the growth of small-scale structure. Say it at the bar like this: add a little mass to the ghost family, and the cosmic web ends up a hair smoother by today, because the ghosts smudge the finest details while sailing past. That's not poetry. It's a measurable tilt on how clumpy things are when you smooth the mass field on certain scales. It shows up as a small suppression in the power spectrum, the graph that tells you how much structure exists as a function of size. And it shows up in weak gravitational lensing as slightly less stretch in galaxy shapes than you'd expect without the ghost's drag. This is where the sky turns into a scale. Particle experiments on Earth can weigh neutrinos directly in a lab by watching how the energy is shared in certain decays. And those numbers put an upper limit on how heavy each type can be. The sky goes after the family total from the opposite angle. If you assume the big picture model we've been using is basically right, then the amount of suppression in small-scale growth places an upper bound on the total mass. The actual bound depends on which measurements you combine and how conservative you are about possible caveats. But the spirit is stable. The sum of masses is not just small, it's small enough to matter. Cosmology cares about the difference between, say, a few hundredths of an EV and a few tenths, because those two worlds grow structure at measurably different paces. And since neutrino oscillations tell us there's a minimum total set by the mass differences, there's a delightful game in play. Push the sky's upper limit low enough and you start to corner which hierarchy. Nature chose whether the heavier two are on top with a light grunt, or the oddball is heavy and the pair lighter. You can hear the particle people and the cosmology people cheering each other on from opposite ends of the lab. There's a second neutrino lever baked into the early universe that shows up under a different nickname, the effective number of light species, often spoken of as how many kinds of very fast stuff were around when the baby photo was taken. The standard model of particle physics says there should be 3 neutrino species floating freely back then. If the sky preferred a value noticeably bigger than 3, it would hint at extra light relics, maybe an additional very light particle, maybe something stranger in the early soup. The ancient glow is sensitive to this because fast, free-streaming particles change how sound waves propagated in the primordial plasma. They alter the phase and amplitude of the ripples we read off the sky today. Imagine tapping a drum and finding the overtones slightly out of place. That's the level of forensic music we're doing with the microwave background. Modern measurements keep coming back with an answer close to 3. Give or take a small uncertainty, which is the sky's way of telling us it's not in the mood for a zoo of extra light species. But give or take is doing real work here. Shrink that wiggle room, and you start ruling out entire families of speculative particles. Leave it large, and you have a door cracked for surprises. If you're wondering how this ties to the tensions we've been circling, how fast the universe is expanding today, and how quickly structure has grown, the neutrino story threads both. More total neutrino mass pulls late-time growth down a notch, which moves in the same direction as those lensing hints of a slightly smoother web. In that sense, letting the ghosts weigh a bit more can soothe one mild headache. The catch is that heavier ghosts also nudge the inferred expansion history in ways that can make the Hubble constant standoff worse if you're not careful. It's a juggling act. You can't just declare, add mass, and walk away. You have to check what that does to the baby photo's ripples, to the galaxy ruler carved in the sky, and to the detailed shape of the power spectrum that surveys are measuring with brutal precision. On the flip side, dial up the early time count of ultra-fast species, and you can push the baby photo inferred expansion rate upward, helping the other tension, but only until the drum harmonics complain that the overtones are wrong. Every lever pays rent across multiple rooms. There's also something deeply satisfying about how specific the neutrino fingerprints are. Free streaming, which is the fancy word for this stuff flies in straight lines unless gravity really insists, causes a particular phase shift in the pattern of acoustic peaks. Those crests and troughs in the glow's power spectrum and in the galaxy ruler signal etched into the large-scale distribution of matter. It's not just more or less structure. It's a tiny sideways nudge in the positions of preferred scales. If you've ever tuned a guitar and heard the beat frequency go to 0 as you nail the pitch, you know the feeling. That phase information is hard to fake with unrelated tweaks, which is why it's such a strong cross-check. A model that tries to fix one problem by waving its hands tends to bump the phase and reveal the cheat. Neutrinos, being what they are, move the phase in the way nature actually does. At street level, the neutrino chapter spills into a bunch of practical astronomy. When surveys like the ones mapping weak lensing report that the cosmic web might be a hair smoother than the most vanilla forecast. They have to ask whether part of that is plain old neutrino mass. It's not glamorous, but it's real, and whether the rest is calibration. When galaxy redshift surveys report the ruler's size and the growth rate, their error budgets now include the ghosts as a line item. Assume a little more total mass, and the best fit numbers shuffle. Assume less, and they shuffle differently. And because the sum of masses affects structure most strongly on intermediate scales, big enough to be cosmological, small enough to notice the ghosts skate, designing a survey becomes a game of where are we most sensitive to the smudge. It's why you hear survey people obsess over window functions and scale cuts with the intensity of chefs arguing about salt. There's a romance to the cosmic neutrino background that we rarely indulge because it sounds like science fiction. Just as the ancient microwave glow is fossil light from when the universe first let photons roam free, there should be an older relic, a bath of neutrinos still washing through us, cooled by expansion to a temperature a hair under 2 Kelvin. We haven't caught that background in a direct, lab-style detector yet. Neutrinos are too aloof for easy traps at those energies. But its existence is woven into the pattern of the cosmic drum in enough independent ways that treating it as real isn't a stretch. It's the sober read. One day, if someone invents a detector clever enough to snag a few members of that ancient bath directly, it'll feel like shaking hands with the universe's childhood friends. Until then, cosmology listens to their footprints in the ripples, and in the way structures' growth slowed just a touch under their passing. What I love most about the neutrino subplot is how it keeps science honest. It's tempting, when you see a small mismatch between forecasts and measurements, to reach for exotic fixes. The ghosts insist you first pay what you owe in standard physics. They are real, they have mass, and they chip away at small-scale clumpiness in a way that looks, on a plot, a lot like some of the fashionable new ideas, but with the advantage of being guaranteed by laboratory evidence. Fold them in carefully, with the right units and the right uncertainties, and some tensions relax while others tighten, which is exactly how you learn what's a calibration story and what might be a genuine hint. And because the ghosts touch every messenger light, large-scale structure, even the ripples in space-time, if black holes merge differently in worlds with slightly different small-scale histories, they force our different microphones to harmonize or confess. If the theme of this documentary is that being wrong, carefully, is how you learn, neutrinos are the friendly correction we've already absorbed. We were wrong to treat them as weightless background noise. We were right to let the sky tell us how their featherweight mass leaves heavyweight signatures. And we're in the middle of the fun part now, where better maps of the lensing sky, sharper galaxy rulers, and cleaner baby photo harmonics keep shaving the wiggle room on their total mass and on how many light species the early universe was hosting. Somewhere between the lab scales and the sky's drum lies a single number how heavy the ghost family is in total that will lock a few doors and open a few others. When it does, it won't be because anyone shouted loudest. It'll be because the ghosts, finally, had no more places to hide. If the first half of the story was, here's what the universe whispered, the closing stretch is, here's who's about to turn up the volume. Think of the next decade as a crowded stage where each instrument plays a different range, and the harmony, if we get it, decides whether the map we've been using needs a tune-up or a rewrite. The vibe is less eureka and more cleaner microphones, longer sets. That's how big arguments get settled in cosmology, not by slogans, but by better data sung in unison. Start with the wide-field eyes that redraw the sky in 3D. A survey camera that stares night after night doesn't just take pretty pictures. It measures shapes so precisely that the barely there stretching of background. Galaxies' weak gravitational lensing pops out statistically. Lensing is the trick where mass bends space and light follows space. So a lumpy universe leaves a faint fingerprint in the ellipticity of galaxies smeared across huge patches. If you can keep track of how the atmosphere and the optics blur a point of light, the point spread function, the instrument's signature, you can subtract the blur and keep the cosmic stretch. Do this over billions of galaxies, and you get the growth history of structure as a function of time. The neat part is how that history talks to our tensions. A slightly smoother than forecast web pushes you one way on the why don't early and late numbers match. Question: a perfectly on-script web pushes you another. Either way, the shape measurements have to be so clean that your own telescope isn't pretending to be the universe. That's why teens go full paranoid with calibration stars, simulations, and blind analyses where the final answers are hidden until all choices are locked. It sounds fussy because it is, and it's the only way the clumpiness scoreboard means anything. Paint over that lensing map with a second layer, the cosmic ruler etched into the galaxy distribution by primordial sound waves, the same early ripples that left their echo in the ancient microwave glow. Observers call it the baryon acoustic feature, and if you say fast enough, friends will still keep listening. The drumbeat is simple. There's a slightly preferred separation at which galaxies like to be found, and that separation, measured at different redshifts, tells you how distances scale with time. It's a geometry test that doesn't care about supernova personalities. And when you pair it with lensing, you get the two halves of a consistency check. One tells you how the room expanded. The other tells you how the furniture clumped. If both halves hum the same tune, the quiet push we've been calling dark energy looks steady. If they drift apart in a pattern, you start asking whether the push has a pulse or whether gravity itself has a quirk on the grandest scales. Closer to the baby picture, new microwave eyes are getting built with a single obsessive purpose: separate the universe's whisper from our galaxy's hum. The ancient glow, the cosmic microwave background, is full of information in both its temperature freckles and its polarization, the orientation of the light's electric field. The polarization carries a special swirl pattern that a lot of people have chased as the smoking gun of an ultra-early sprint called inflation. The catch is that interstellar dust in our own Milky Way produces polarized microwave light too, and with a mischievous spectrum that can masquerade as the swirl if you're careless. So the plan is straightforward and unsexy. Observe the same patches in many microwave colors. Map the dust and magnetic fields with indignantly fine detail, and subtract them until the only swirl left is either the universe or the hum of your instrument. If that swirl turns out to be real at a convincing level, it would be like hearing the drummer's ghost note from the opening bar of the song. If it doesn't, the absence is a result too, sandpapering away flamboyant early universe models and steering us toward plainer ones that still fit the rest of the sky. Swing to a different wavelength, and the conversation changes from oldest light to first neighborhoods. Neutral hydrogen, the most common element in the cosmos, has a radio whisper at 21 centimeters. You can't see it with your eyes. You can map it with radio arrays that tile the sky. The trick is that this whisper traces where the gas lives across time, including the murky era when the first stars and galaxies switched on and rayonized the universe, flipping the fog back to a transparent medium. If you can build a clean 3D map of that whisper across redshift, you don't just watch the lights come on. You also get a new set of distance and growth measurements that live far from the usual optical surveys. It's like adding a bass guitar to a band that used to be all trebly. The practical headaches are Sirius Earth is loud at radio frequencies, and the instrument calibration has to be monk-level disciplined. But the payoff is a volume of space so huge that cosmic variance, the universe's own coin flip noise, finally starts to shut up. On the closer, Messier end, the telescopes with acreage-sized mirrors are basically time machines with better handwriting. A giant mirror plus sharp infrared vision lets you take spectra spread, a galaxy's light, into its rainbow, so you can measure redshifts the honest way and nail down which two grown-up too early candidates are truly as far as they look. Spectra also show you the fingerprints of elements and the strength of emission lines from star-forming gas. Two clues that help you stop overestimating masses because a neon line slipped into the wrong filter. Catch the Balmer break cleanly. Catch Lyman alpha dodging its way through hydrogen fog. Catch oxygen yelling from H2 regions. And your uncertainty on how old, how big, how dusty shrinks from shrug to sentence. That's how you turn the early galaxy hubbub into either calm down, we were fooled by selection and glow, or okay, star factories really did run hot. Adjust the recipe. The arbiters in the Hubble constant fight, the slope of expansion today in kilometers per second per megaparsec will arrive with wonderfully different flaws. Distance ladders will get sturdier bottoms from parallax, the geometry method, where a star's apparent position shifts by a tiny angle as Earth orbits the Sun, and those bottom rungs will anchor not just one, but several mid-rungs. The pulsing Kepheid stars, the tip of the red giant branch, the graininess of galaxy light called surface brightness fluctuations. At the top, the supernova that read the slope will sit and host galaxies whose properties we know too well to let environment sneak in an extra percent. On the early universe side, the cosmic ruler in galaxy maps, combined with the baby photos recipe, will keep tightening the prediction for today's slope as the data volume grows and the foreground modeling gets less romantic. And then there's the referee we can't sweet talk, gravitational wave standard sirens. When two neutron stars merge, the loudness of the space-time ripple tells you distance, full stop. If you also spot even a whisper of light from the same event, you get the redshift, and you have a point on the distance redshift curve that doesn't care about candles and rulers. 1 point is a curiosity, a dozen is a conversation, 100 is a verdict. 2 more ideas hover just off the stage lights, patient and rude. 1 is redshift drift, which is exactly what it sounds like. Stare at exquisitely sharp spectral lines in very distant objects for long enough, and the ongoing expansion should slide those lines by a tiny amount in real time. You need ridiculous stability, years of it, and a tolerance for boredom. But the payoff is that it's the universe itself telling you the slope changed by this much this decade, without anyone translating early ripples into late time numbers through a chain of assumptions. The other is gravitational waves from the heavyweights mergers of massive black holes in the centers of galaxies, which will hum at frequencies far below what current ground detectors can hear. Catch those space-based notes, and you get a growth census of the very engines we argued about when we asked how early quasars got so big so fast. See a merger at high redshift, and you've found a courthouse record from the frontier. Maybe the most important upgrade isn't any single telescope, it's the handshake between them. When the lensing people say, the Webb looks a hair smoother, the galaxy ruler people contest whether distances bend toward a slightly different arc that makes the two consistent. When the latter insists on a faster today, and the baby photo implies a slower one, the sirens can cut through the middle. When radio maps of hydrogen sketch with the fog lifted, infrared spectra can name the culprits that lit the match. When microwave polarization tiptoes toward or away from a primordial swirl, the dust maps from our own galaxy explain how badly we were being catfished by foregrounds. None of these handshakes is glamorous. All of them are how grown-up science works. I get that the next decade of surveys doesn't sound as sexy as we were wrong about everything. But here's the plot twist. The new instruments are designed precisely to tell the difference between we missed a 1% calibration and the early universe ran a tiny side hustle without flinching. They'll do it by being redundant on purpose, by measuring the same quantities in ways that fail for different reasons, and by publishing their plumbing so cleanly that strangers can come in and rerun the pipes. If this sounds like an ode to boredom, it's because boredom is secretly how discovery happens. When the instruments get so steady that the only wiggle left is the sky itself, whatever refuses to go away after all the boring checks is the real clue. So here's the bar napkin version of where this leaves us before we swing into the synthesis. The universe owes us nothing but consistency. We're about to ask for it with sharper eyes, steadier hands, and microphones that don't hum. If the map we've trusted holds, the numbers will finally shake hands. Expansion slope, growth rate, early recipe, all nodding in the same key. If something small but stubborn keeps refusing, it won't be a headline. It'll be a line that stayed put while everything else got cleaner. That line will be the scene where the next update slips in, not to burn the bakery down, but to fix the oven by exactly the amount the cake needed. All right, cards on the table. We've spent hours with coffee going cold, chasing threads that ran from baby pictures of the cosmos to neon quasars and whispering neutrinos. And the question that started this whole thing still sits between us like a dare. Were we wrong about the universe? The honest answer, said with a grin rather than a wince, is that we were wrong in the way a good map is wrong useful, beautiful, and off by just enough that the best way to honor it is to redraw a few streets. The plot twist isn't that the big picture collapses. It's that the small scenes where facts refuse to shake hands point to the upgrade. Take the expansion fight. One tradition reads the slope today by building a distance ladder rung by rung, from geometric parallax to pulsating stars to supernova, and lands on a faster expansion. The other tradition reads the early recipe from the ancient microwave glow and the cosmic ruler, carved into galaxy clustering, and lands on a slower expansion. Both camps have done the grown-up thing. Blind analyses, boring calibrations, swapping data, letting strangers rerun the pipes, and the gap survived. Meanwhile, a different argument hums in the background about how lumpy the cosmic web ought to be by now. The early recipe forecast and the late-time lensing measurements don't always hum in the same key. And just when we think we've boxed that up, baby galaxies show up looking suspiciously mature, and black holes barely old enough to rent a car somehow weigh 1 billion suns. If this were a movie, this is the scene where the detective pins string from clue to clue, and the mess suddenly forms a picture. The picture that makes the least drama and the most sense has two versions, and I want you to feel both. In the first version, the universe is conservative, and we were cocky. A few small biases hid in plain sight. Crowding made some Kiphides look a touch brighter. Dust in other galaxies behaved a hair differently than our favorite model. Selection nudged our supernova sample toward the show-offs, and one of the mid-rungs of the ladder leaned by a percent that amplified at the top. On the other side of the aisle, the translation from the baby photo to today's slope borrowed a conversion factor that assumed the early soup was exactly as simple as we like to say, when in reality, a whisper of foreground or a sliver of modeling choice nudged the inference. Clean those up. Let gravitational wave sirens weigh in with their brand new accent that doesn't care about candles or rulers, and the two numbers finally shake hands somewhere in the middle. At the same time, the smoother than forecast hints in the lensing maps relax as shape measurements get cleaner and galaxy samples get wider. The cosmic web feels like the forecast table under your palm again. The early heavyweights slim down once spectra catch the emission lines that photometry misread as mass, and the remaining honest overachievers turn out to be exactly what they should be in a rowdy, low metallicity nursery. Top-heavy star factories feeding black holes in short, super Eddington bursts. In that world, the update is deliciously boring. The map stands, the decimals move. The headline is that humility beats hype. But the second version, the one that keeps us up in the best way, is that after every calibration you can think of, something small and stubborn refuses to go away. Not a revolution with fireworks, a seam, a line in the plot that stays put while everything else gets cleaner. If that happens, the most economical bridge between the early recipe and the late-time readings looks like a tiny extra plank installed early on. You don't blow up the kitchen. You add a spoonful at the right minute. A brief, subtle puff of energy before the universe's first big photo would shift how large the ancient ripples appear without wrecking the rest of the pattern. Nudging the baby photo inferred expansion, upward toward the latter's value. That puff would have to turn on and off with comedic timing and pay rent across the hall. I'm not trashing the polarization of the ancient light or the later growth of structure. If it passes those tests, suddenly two fights cool down at once. Meanwhile, the smoother web whispers might be partly the ghosts. We already know the neutrinos pulling growth down a notch because they skate through shallow gravity. Wells when they're young and fast, plus a hair of genuinely time-dependent push in the late. Universe that changes the growth slope by an amount so small you'd miss it if your lensing maps weren't ridiculously clean. In that world, the map still stands, but it gets a new legend, an early time tweak that ages out, and a late time push that isn't perfectly deadpan. What's beautiful about both versions is that they make precise, dull predictions. In the conservative world, as sirens accumulate and radio maps of neutral hydrogen paint a 3D mural of the web, the slope today migrates into a shared window and stays there regardless of which instrument sings. The growth numbers derived from weak lensing and from galaxy motions click into the same key once shape and selection. Systematics are caged. The early galaxy census looks less shocking once spectroscopy boxes out the sneaky emission lines and lensing magnifications. The hunt for primordial swirls in microwave polarization stays quiet or lands only at levels that favor the planar, smooth and simple versions of the early sprint. In the small new thing world, sirens point a little higher than the baby photo conversion alone predicted. The ruler carved in galaxies, and the lensing growth curve develop a tiny, coherent kink as a function of redshift that refuses to be fit by a constant push. The polarization of the ancient light permits a whiff of early time mischief without inviting dust to masquerade as a signal. Neutrino mass deductions from the sky settle at the low end of what labs allow, but not zero, just enough to keep the web politely smoothed. Neither version gives you a tweet. Both give you cross-checks. And those overachieving babies, the early galaxies and the ravenous black holes, are the perfect tiebreaker. If they're mostly mirages of bad assumptions, then the new spectra will make them moderate. Their masses nudge down, their colors unmask the role of emission lines. And the reionization budget, the ultraviolet light needed to flip the fog back to transparent or look like many fireflies rather than a few flashlights. If a stubborn core of them stays truly massive and luminous disgustingly early, the universe will have told us, quite politely, that its opening factory ran hotter than our default recipes allowed. Not everything was wrong, just the part where we assumed the newborn nursery plagued by adult rules. Direct collapse seeds form in a handful of privileged neighborhoods where fierce ultraviolet light suppresses fragmenting. A few feeding binges go super Eddington for a minute. Mergers bring engines together earlier than our gut allowed. And the signature shows up, not as a single smoking gun, but as a pattern. A blue-tilted continuum here. A broad line with the right wind profile there. A lensing magnification you can measure and subtract. A radio whisper that says dust didn't do the heavy lifting. Either way, the fix ripples through the rest of the map without breaking it. So was everything we knew wrong? Only in the sense that everything is too big a word for a field that prides itself on earning details. Space really is expanding, not because raisins race through dough, but because the dough rises under the raisins. The ancient afterglow really is the universe's baby photo, and the freckles in that glow really pin down the early recipe with a rudeness that would make a dinner guest blush. Invisible scaffolding really shapes where the light lives. Call it a particle we haven't caught yet if you like elegance. Call it a tweak to gravity if you like drama. But the lensing maps and the motions of galaxies and the distribution of clusters all point at extra weight doing quiet work. The late time push that bends the arc of expansion from braking to gently accelerating is not a mood. Its distances coming out larger than a coasting universe would allow. Neutrinos really do carry mass that is tiny for a lab and not tiny for a sky. Inflation or something very much like it really does read as the smoothing that set the stage and planted the seeds. Even if the drummer's ghost note of primordial gravitational waves stays coy. Those are the bones. The meat that needs work is the handful of percent-level scenes where honest, independent microphones disagree. And if you're looking for a philosophy to take home, it might be this: the way science says we are wrong when it's healthy is by getting precise enough that the wiggles can't hide, then refusing to let personality decide which wiggles matter. That's why the new instruments don't just promise more. They promise cleaner. They promise sirens that don't care about brightness, rulers that don't care about candles, lensing that doesn't care about galaxy color, baby photo polarization that doesn't get catfished by dust, radio maps that don't need to love starlight at all. They promise, in other words, that whichever small fix the universe is nudging us toward will be the one that survives every boring test we can throw at it. If the fix is a calibration, it will be exposed by its own narrowness and celebrated for the craftsmanship it took to find it. If the fix is a sliver of new physics, a brief early puff, a barely time-varying push, a whisper of conversation in the invisible sector, it will stop hiding once the microphones stop humming. Here's the last thing I'll say before we slide into the wrap-up. The sentence, "We were wrong about the universe," is only worth saying if it makes the next sentence better. The next sentence here is already taking shape. Either we learned that our instruments and methods needed one more notch of honesty and the map clicks into place, or we learned that the cosmos ran a small side hustle at an hour we hadn't accounted for, and the map gets a new, elegant contour. Both are wins. Both make the story truer. Both make late-night coffee taste better, because you're not just being dazzled by a big idea. You're watching a community argue with reality until only the sturdy bits remain. That's how you go from a tidy myth about a hot beginning and invisible stuff to a grown-up narrative with time stamps, uncertainties, and enough humility to admit that wrong is just the cover charge for getting closer. If you've made it this far, you've basically done cosmology the way the grown-ups do it. Not by memorizing sacred numbers, but by living with the delicious discomfort that the best answers arrive with smudged fingerprints and a few coffee rings. We started tonight with a mischievous title and a promise not to hide the mess. The mess turned out to be the point. Space really is expanding, think dough rising, not raisins sprinting, and the universe really did leave us a baby photo that's more honest than our moods. Invisible scaffolding shapes where the light lives. A quiet push speeds the late-time stretch. Ghostly particles shave a little texture off the web, and the opening act very likely smoothed and seeded everything before the first stars blinked on. None of that fell apart when we poked it. What cracked open, instead, were the seams that matter. A slope today that reads a touch high from the local yardsticks and a touch low from the early recipe. A web that sometimes feels slightly too smooth for the forecast. A handful of precocious galaxies and black holes that show up ahead of the schedule we penciled in. Those aren't scandals. They're invitations. They're the places the universe taps the mic and asks if we're listening. A grown-up move was never going to be choosing sides like a sports bar. The grown-up move is the thing we watched, chapter by chapter. Measure the same truth with microphones that fail for different reasons. Lock your analysis before peeking at the score. Let strangers rerun your pipes, and then only believe what survives boredom. When that culture meets the sky we actually have, two endings become possible, and both feel like a win. In one, we catch the last gremlins in our distance rungs and foreground models. Sirens weigh in with a voice that doesn't care about brightness. The early recipe and the late measurements shake hands in a shared window. The web's smoothness reads like the forecast table under your palm. The overachieving babies slim down just enough once spectra stop being fooled by pretty emission lines and lucky magnifications, and we close the book with better decimals and better posture. In the other, after every calibration you can name, a small but stubborn line refuses to move. Then the upgrade is a spoonful, not a bonfire, a brief early time puff that ages out without mangling the baby photo, a push that is almost constant but not perfectly deadpan, A whisper of conversation in the invisible sector that trims growth by just the right hair. The ghosts carrying exactly the mass the map will eventually confirm. Either way, the map gets truer. Either way, we were wrong cashes out as we are less wrong, which is the only currency science accepts. It's tempting to leave it there with a neat bow and a wink, but I don't want neat. I want you to feel how human this is. People built instruments that argue with the air and the optics before they dare argue with the cosmos. They sat in domes at ugly hours, watched their plots wobble, and chose discipline over drama. They published pipelines like cookbooks, so future strangers could spot the pinch of salt that made a percent look like a revelation. They learned to love blind analysis because it keeps your hands off the scale. They chased rumors and let them die in the daylight because the baby photo didn't blush the way the rumor needed it to. They disagreed like professionals and then merged datasets like adults. If there's a moral here, it isn't that the universe loves us. It's that the universe is consistent, and we can be too if we're stubborn in the right way. So what do you do with that, sitting at home, not planning to build a telescope or debug a pipeline? You treat big claims the way astronomers treat pretty pictures. You ask how many microphones heard the same note. You notice the plus or minus on numbers and respect it instead of rolling your eyes. You keep two ideas in your head at once, that humility is a virtue and that curiosity is a responsibility. You learn to enjoy the sentence that begins, "We thought X, and we measured better. Now it looks like Y," because that sentence is how everything important gets better, from medicine to engineering, to whatever you want the future to look like. If cosmology feels like a faraway game, remember that the habit you practiced here, refusing to be impressed until cross-checks agree, is portable. It works on headlines. It works on hunches. It even works on your own favorite stories. And because this is still YouTube and not a faculty meeting, I want to leave you with a bet to argue about in the comments. If you had to pick today, with the evidence on the table and the instruments lining up for their next decade on stage, where would you put your chips? Does the Hubble slope standoff fade when a cleaner ladder meets a stricter early recipe and the sirens break the tie? Or does a small, elegant tweak early time spice? A barely time-varying push, a whisper in the invisible sector, earn its place because it stitches two headaches at once without ripping anything else? There isn't a wrong answer tonight. There's only the answer you'd be proud to revise when the next round of data walks in and refuses to flinch. If you felt at home in this booth, hit subscribe and keep a seat warm. I don't want this to be a one-off monologue. I want a running argument with reality that we have together. Drop a comment with your bet on the fix and tell me why calibration cleanup or small new physics. And give me one measurement you think will decide it. Sirens, lensing, microwave polarization, 21 centimeter maps, time delay lenses, redshift drift. Don't just say the word, say the why. Then pitch our next mission. Do we dive headfirst into the cosmic dawn and build a street-level tour of how the first neighborhoods lit the fog and rayonized the universe? Do we go full detective on black hole origin stories and try to catch a direct collapse seed in the act? Do we take a night for the neutrino ghosts and follow their footprints from the lab to the sky until the family total has nowhere left to hide? Or do we get weird on purpose and ask what it would take for gravity to look different in a way that passes every test without acting like a diva? Your vote genuinely steers this channel. The best episodes we've made started as a dare in the comments. If you're still here, you're my kind of person, which means you know this isn't a cult of certainty. It's a club of good questions. The title we started with was a taunt, and we lived up to it the responsible way, not by burning the textbook, but by underlining the margins where the next paragraph belongs. I'll keep bringing the late-night coffee and the analogies you can hold without a calculator. You bring the skepticism that smiles and the patience to let boring checks do their job. Somewhere between those two, the universe will give up a little more of its script. And when it does, we'll be here in this booth with the neon humming, turning "We Were Wrong" into a better story about why it was worth being wrong in the first place. If that sounds like a deal, tap subscribe, ring the bell so the next episode doesn't hide from you, and tell me your bet and your next target. I'll be reading, arguing, and stealing your best ideas with attribution and appreciation. The cosmos won't wait, and neither should we. Let's go find the seam together and pull gently, persistently, until the new shape appears.